Yeah, hi everyone. So finite state machine. So this was the requirement from you guys. You were saying that you need the video on FSM. So after getting a very good response on STA, so if you are someone who is directly coming to FSM, you can watch this STA video as well. I'm not saying that STA is the prerequisite, but you can watch the STA video as well because this will also help you. Because if you are looking for FSM, that means you would be looking for STA as well. So this video got a very good response. So similar response I will be expecting on this FSM video as well. If you find it helpful, you can comment down. So this is the only thing I'm expecting from your side. What is that? Just like the previous video, I will expect the comments. So once you are done watching this video, you can comment down. Okay. And secondly, this video will be of roughly around 5 hours, but it will not take you that much of time. If you are not making your own note, then I guess in 4 hours you will be able to complete this 5 hours of content. And if you are making your own note, then I guess it would take you 5 to 6 hours. Okay. So it will not take you much time. Just try completing it in one go only. Okay. Just sit for 3 to 4 hours or 5 hours and then try completing it, the complete concept of FSM. So right from the scratch we are starting, like whatever the, like how from sequential circuits we are moving towards FSM, what is the problem it is solving, why we needed the FSM. So that kind of scratch we are starting from. And if I say one prerequisite, then the prerequisite would be that basics of sequential circuit should be clear. Like at least very basic you should be knowing that what is the meaning of D flip flop, T flip flop, JK flip flop, SR flip flop. So that much basic you should be required. Okay. You might have covered it on surface level, or you might have covered it on semester level only. You have studied for gate, for anything, but very basics of sequential circuits are required. Then only you will be able to understand finite state machine, right? And let's do the promotion. I will do the promotional part. So we have this course, digital VLSI mastery. So in this course, almost whatever that is required for digital design placements, so that thing we are covering. Starting from the basics, in basics we have covered Boolean algebra and all these kind of things. Basics of digital electronics, then number system, K-maps, combination, sequential, STA, FSM, data converters, some RC circuits, CMOS, all these will also be required, Verilog, COA. So whatever that is necessary, most of the part, like 95% of the part we have covered, because I cannot say 100%. Why is that so? Because digital is a vast field, right? Digital is a vast field. No one ever can cover 100% of digital design, right? Ever 100% cannot be covered. So whatever that has been covered on surface level, I have wrote down here. If you want to know the depth, that what single topic has been covered, so topic by topic I have told here. This is just the chapters. Like this is a basics is a chapter, number system is a chapter. Now in each chapter, what all topics we have covered, that has been wrote down in this particular video. So you go to YouTube and type digital VLSI mastery cohort 0200 course launch. In that manner you type, you will get this video. In this particular video, whatever that has been taught, all the topic has been mentioned. So you can first watch this video, then you can come to this particular course if you want to buy it. So link will be posted in the description box only. So if you want to purchase it, you can purchase it. You can apply the code Titans10. Okay, Titans10. I guess it would roughly cost you around 3.2k, 3200. I don't think more than that it will cost. So roughly around 3200 it will cost you. So you can apply this code Titans10. Okay, Titans10. Titans10. So if you want to purchase it, you can purchase it. Otherwise, if you want to study from YouTube, then enough resources I have given, you can study from there as well. So this is something where I personally have taught. So you can watch this launch video. In this launch video, everything has been told, what all things have been taught. And after that, if you want to come to this course, then you can come. So let's get started studying about FSM. Thank you very much. And I would be expecting comments from your side. Thank you. Hi everyone. So from this video onwards, we will start studying about FSM. FSM means finite state machine. So on the top level, what is the definition? So it is a simplified model to represent sequential circuits. So FSM is nothing but sequential circuits only. Okay, so we will see the block diagram, we will see the types as well. But let's just study whatever that we have studied. We have studied combination circuit. What was the combination circuit? The outputs were depending on the applied input. Whatever the input you apply, based on that you will receive the output. We saw a lot of example: full adder, half adder, multiplexer, demultiplexer, even a simple XOR gate, even a simple NOR gate, even a simple OR gate or AND gate. These are also your combination circuit only, because let's just say this is the AND gate. So here if I apply 1 0, my output will be 0. So based on this input only you are receiving the output. If you apply 1 1, your output will be 1. So this is also a combination circuit only. So combination circuit is simply a circuit where your direct output will be depending on the applied input. Then we studied about sequential circuits. So in sequential circuit, what was the scene? In sequential circuit, we have studied about counters and different kind of counters we have studied in sequential circuit till now. Okay, so what was the scene there? There was a combination circuit and there was a memory element. So some part of the output of the combination circuit was fed back to the memory element, and whatever the output was there of memory element, that was fed back as the input to the combination circuit. We can take a simple example. This is a D flip flop, Q and Q bar is there. Let's just say this output is this output of memory element. This is a memory element which is clocked here. This is a memory element. Memory elements are flip flops and latches. So we are talking about flip flops. Now let's just say it is fed back to the input in this way. Okay, this is a D flip flop. Output of this is fed back to the input, and this is how we can represent it, right? So a combination circuit is there which is an inverter. Output of this is fed back as the memory element here, and this output, whatever the output has been received here, that has been fed back as the input to the combination circuit. Output of combination circuit is fed back as the input of memory element, and here if you see, the output of memory element is fed back as the input to the combination circuit. So this was one of the examples. These kind of examples we have already seen. So this is one of the combination circuit. If you design a sequential circuit, one of the sequential circuit. If you design any counter, there you will see that there are a lot of elements involved. There will be gates as well. There will be these memory elements as well. Okay. So this is what we call as sequential circuits. Now we are going to study about FSM. So in FSM, there will be two types, Mealy and Moore. Both will have different models. So let's check out about Mealy model. So first we will study about Mealy machine. So this much of circuitry you have already studied. This was your sequential circuit only, right? Input is there, output is fed back to the memory element, and output of memory element is fed back as the input of the combination circuit. Now in Mealy machine, what will be the scene? We will have a different output logic. We will have output logic which will have two inputs. This output logic will have two inputs. One will be the applied input, this input, applied input, and other one will be the present state of memory element. Present state of memory element. Okay, so the output Y will be a function of present state of memory element. That means that would be some Q, Q0, Q1, Q2, Q3 it would be, and input X. And what is our next state? Next state Q plus. Q plus. It is certainly a function of input X and Q, right? We took this example. Although here there is only one thing, that Q plus, what Q plus will be equals to? Q plus will be equals to D, and D is Q bar. So here it is only a function of D bar, but if there was some other input, let's just say if this was SR, so what will be Q plus? Q plus will be S plus R bar Q1, and R I am putting as some X, R I am putting as some X is there, okay? So what will be your Q plus? What will be your next state? Your next state will be S which is Q bar plus R bar X bar Q. So this will be your next state, Q bar plus X bar Q, and where it can be reduced at Q bar plus X bar. So next state is always a function of Q and X, the applied input, right? If two different inputs are there, so your next state would be function of those two things. So whether it is Mealy machine or Moore machine, the next state Q plus will always be a function of applied input and the past state, or you can say present state. If this is next state, then this I will be calling as present state. Basically, I will call my Q plus as next state and Q as present state. Okay. So this is your Mealy machine. We will see example, it will be more clear to you. So this is the example. What you can see here. These are the memory elements. Memory elements. Let me do one thing. So these are the memory elements. Certainly these will be clocked. So which I should have already shown. There will be certainly a clock, right? So both will be clocked. Okay. So these are the memory element. This is the combination circuit. This is the combination circuit. So this complete circuit, this much of circuit, this is what? This is your sequential circuit. You can see the output of memory element is being fed as the input to the combination circuit, and output of combination circuit is fed as the input of the memory element, right? Output of memory element is fed back as the input to the combination circuit, and output of combination circuit is fed back as the input of memory element. Now here there is different one more output logic. This is your output logic. This is your output logic. Now here you see an output logic, and your output logic y is a function of input x and this output. What is this output? This output is q0 into q1. This output is q0 into q1. Q0 is coming from here, q1 is coming from here. Q0 into q1 and input x is there. So your y is x plus q0 q1. So it is a function of x and q0. Certainly it is a Mealy machine. Mealy machine. Okay. I will tell you a method also to remember, but let's first study about Moore machine now. So in Moore machine, the complete circuit is same. This circuit, complete circuit is same. What is the difference? Only difference is the output is only a function of q. That's it. Where q plus is my next state and q is my present state. Okay, right? So this is a function of q, and here next state is always a function of q as well and x as well. Okay, so sometimes you can get confused in let's just say there is a question available, okay, and you need to click on correct options. So first statement, in Mealy machine the next state is a function of present state and the input. Correct. The next state is a function of present state and input. In case of Mealy machine, the next state is a function of applied input and present state. Correct. In case of Mealy machine, the output is a function of present state and the applied input. This is also correct. Output is a function of present state and the applied input. In case of Moore machine, the output is a function of present state only. The output is a function of present state only. In case of Moore machine, the next state is a function of present state and the applied input. Yes, that is correct. Because usually what people remember is that in Moore machine, like output will depend on present state only. Output will depend on present state. This is what people remember. But they forget the fact that next state will certainly depend on the present input and the present state. The next state q plus is coming from the sequential circuit, not from the finite state machine. Till this point you have already studied. So this was always a function of q and x, no matter whether you are studying Mealy machine or Moore machine. So you can get confused between this statement, whether it is Mealy machine or Moore machine. Your next state will always be a function of present state and the applied input. Okay, so this statement I am writing, whether it is Mealy machine or Moore machine, next state is always a function of present input and present state. Okay, so sometimes like in temptation, if someone is asking you, in case of Moore machine, your next state will be a function of what? You would say only the present state. This is what people will say, because the difference is in the output logic. The difference is in the output logic. Here, output logic was the function of applied input as well and the present state as well. But in this case, output logic is only the function of present state. So difference is there in the output logic, not in the next state. So this is an important point which you need to take care. Okay. So next state is the same for both, but the output logic will always be a function of applied sorry, output logic will always be a function of present state only. It has nothing to do with the applied input. So this is known as Moore machine. Okay, so how will you remember it? Mealy, this is the spelling of Mealy, and Moore, this is the spelling of Moore. So in Mealy, what you get? L, and L stands for life. In life, your output will always depend on more than one thing. Okay, it will never depend on one thing. Let's just say if you are very hardworking, so is that sure that you are going to get a good rank in GATE examination if you are hardworking only? No, you have to be smart as well. Okay, a lot of people will not agree with this point that sir, hard work will always beat the talent. Yes, hard work will always beat the talent, but in competition examination, you need aptitude as well. You need to be smart as well. So in life, your output will always depend on more than one thing. So in Mealy machine, your output will depend on two things. What are those things? Present state and the applied input. And then Moore machine, it will depend on only one point. Only one thing. In Moore machine, the output will depend on only one thing, that is the present state only. So this is how you can remember it. Okay. It's like competitive examination. Mealy is equals to life. Life is a competitive examination where whatever the input you apply, also your present state, both will decide the output. Moore machine, here only the present state will decide the output, no matter how much input you apply. Okay, so that's the way you can remember it. Okay, Mealy, L is there, so L stands for life. So from there you will be able to remember it. Okay, so in 1 mark question these kind of statements can come and you need to click on the correct statement. So that question we have already seen. I just told that you need to mark the correct option. So we talked about 4 options and all 4 were correct. Okay, so those kind of questions can be asked in 1 mark for true false only. Okay, let's see the example of Moore machine. So what is the example? This is the combination circuit. Same circuit is there. Combination circuit. And these are clocked memory element. This should have been clocked. These are memory element. And this is your output logic. Right? What is your output? Output is Q0 into Q1. So output is only a function of Q. Right? It is not depending on input X. No matter whatever your input is there, it will not depend on that. It is only depending on present state. Okay? Till now it is all clear. So in 15 minutes we have already only seen the introduction. Right? Combination circuit we have studied, sequential circuits we have studied, then we study about there are two models, Mealy machine, L is there, that means output will depend on the present state as well as the applied input. This was the example, output is depending on the applied input as well as the present state. In Moore machine, output will depend only on the output will depend only on the present state. So this was the example where output was only depending on the present state. It has nothing to do with the applied input. Okay. Now we will see there are 3 terms related to FSM. There are 3 terms which are state diagram, state table and state equation. We will see the meaning of each one by one. On the definition, it is a pictorial representation of FSM. State table, tabular representation, and state equation, this is the algebraic representation. Okay, so already you know the meaning of these because we have seen these terms in our sequential circuits only. When we are studying sequential circuit, we have already seen these terms, right? Say yes or no? Yes, we have seen these terms. Just a way of representation will be different. So let's study about state diagram and state table. So this is how a state diagram will look like. So this is a Mealy machine. How will you read this state diagram? Okay, how will you read this state diagram? So these are shown as states. This is known as state. Okay, this is known as input X, and this is your output Y. Basically it will be shown in this manner, X slash Y. This will be your input, this will be your output. Input, output. This will be your input, this will be your output. Well and good. Okay, so and A, B, C, D, these are known as state. So this is input, output, and this is a state. This is a state. Okay, So how will you read it? If you are currently in state A, and the applied input is 1, then your next state will be A only. You see the arrow. If my applied input is 1, then my next state will be A only and my output will be 0. Now I will ask you the question. If your present state is A, let's write it here. If your present state is A, your applied input is 1. Then your, okay, this I have already seen that my applied input is 1, then your next state will be A only and output will be 0. Okay, let's write down for this. If your present state is A and applied input is 0, present state is A, applied input is 0, then your output will be 1 and the next state will be B. So from A to B you are going when your applied input is 0 and your respective output will be 1. Now, if your present state is B and applied input is 0, then your output will be 0 and your next state will be B only. Okay. If you are in state B and applied input is 1, then your next state will be C and respective output will be 0. Let's see this one. If your present state is C and applied input is 1, then your next state will be C only and output will be 0. If you are in C, if you are currently in state C and applied input is 1, then your next state will be C only and output will be 0. Let's talk about this. If you are currently in state C, applied input is 0, then you will go to state D. Applied input is 0, then you will go to state D with respect to output which is 1. You will go from C to D if your applied input is 0 by giving the output 1. Say yes or no. What about this D? If you are currently in state D, and your applied input is 1, then you will come back to D only by giving the output 1. Okay. What else you can write? If your current state is D and your applied input is 0, then you will go to state A by giving the output equals to 0. Say yes or no. Is that clear to you or not? Shall I explain once again? I will pick anyone. I will pick this and explain it again. If you are currently in state C and your applied input is 0, for state C, two are going outward. This is also outward and this is also outward only. So if you are in state C and your applied input is 0, then you will go to state D by giving the output 1. C, applied input is 0, you will go to D by giving the output 1. So this is how you read a Mealy machine. Okay, in Mealy machine, your output is depending, this is a Mealy machine, right? So output is depending on the applied input as well. Here, if I apply input 1, my output was 0. And if I applied input 0, my output was 1. So your output depends on the applied input as well. Here it is depending on the applied input. So certainly it is a Mealy machine. Let's see the example of Moore machine now. So this is how it will look like. So A then 0. So what does it represent? This is the state and this is output. And this is your applied input. So this is how you represent Moore machine. So in Moore machine, your output should not depend on the applied input. So if you are in state A, then no matter whatever the input you apply, if you are currently in state A, then no matter whatever the input you apply, your output will always be equals to 0, irrespective of the input applied. But if applied input is 0, if applied input is 0, then your next state will be A. And if applied input is 1, then your next state will be B. Because what did I tell you? Your next state is a function of Q and the applied input. And your output Y will always be a function of only state, which is state A. So if you are at state A, then your output will be 0, that's for sure. If you are at state B, then your output will be 0, that's for sure. If you are at state C, your output will be 0, that's for sure. If you are at state D, then your output will be 1, that's for sure.
So this output is not depending on AB, it is not depending on the applied input. Okay, it is only depending on the present state. That if you are at A, certainly your output will be 0. If you are at B, certainly your output will be 0. If you are at C, certainly your output will be 0. If you are at D, your output will be 1. Now what will be the next state? So if you are at state A and applied input is 0, you will come back to state A only. And if applied input is 1, you will go to state B. If you are at state B, applied input is 0, you will come back to B only. But if applied input is 1, you will go to C. If you are at state C and applied input is 1, then you will come back to C. If you are at state C, applied input is 1, you will come back to C. And if your applied input is 0, then you will go to state D. If you are at state D and applied input is 0, then you will come back to D. And if applied input is 1, then you will go to A. There you go. So this is how you write it down. Okay. Let's take another example. Let's take this example and I will explain it again. If you are currently in state D, then certainly your output will be 1. But if the applied input is 0, then you will come back to state D, and if applied input is 1, then you will come back to, then you will go to the state A. So this is how we read it. Is that clear to you? Okay. So this was Millet machine and Moore machine. So here you can see the output was only a function of Q. And in this example, what you can see, your next state will always be a function of next state. Here you can see from A to B you are going. So next state is certainly a function of Q as well, present state, as well as the input applied, So no one can change this. But here your output is a function of, here your output is a function of present state as well as the applied input. With respect to different input, it will have different output. But here, with respect to different input, or output is same. Whether you are applying x equals to 0 or x equals to 1, output will be 0 only if you are in state A. Okay. Now we will see the example. We will see examples. We will design FSM. But before that, let's study a simple topic which is state reduction. Because when we study about designing our FSM, when we design our FSM, there this concept will be used. So state reduction means you need to remove the redundant state. There will be some redundant state that you need to remove. So this particular FSM is given. First tell me, it is a Millet machine or Moore machine? Millet or Moore? It is a Millet machine. Why it is a Millet machine? 0 0 1 by 1 1 by 1. If something like this is written, this would be Millet machine only. You can see it would be Millet machine only. Here this will be Moore machine. In Moore machine you will not find 1 by 1 or anything like that. Okay, 0 by 1, 1 by 0, 1 by 1. These you will not find in Moore machine. Or you can read this as well. How you can read this? What you need to find? How your output will depend. So output, if you applied input 0, your output will be 0. If you apply input 1, your output will be 1. So your output is depending on the applied input. So certainly it is a Millet machine. Or directly you can remember, if 1 by 1, 1 by 1, 0 by 0, 1 by 0, if these kind of things you can see, that means certainly it is a Millet machine. Now you draw the state table. Now. Okay. You will certainly understand what do you mean by removing the redundant state. If you draw the state table, just draw the state table. What you are going to write? Present state, next state with respect to the input x equals to 0, x equals to 1, and output with respect to x equals to 0 and x equals to 1. Just write it down. So this is how you must have written it. Let's take this example. Okay. Let's take example of D. Let's take example of D. So if my present state is D and applied input is 1, then my next state will be F by giving the output 1. If my present state is D and my applied input is 0, then my next state will be E and output will be 0. Say yes or no. This is what I have written. EF 0 1. So based on that you can write down this particular table. Okay. Now what do you see here? What do I mean by redundant state? What do I see here? Here, if you see A and C, these two rows are exactly same, A and C. DB 0 1 0 1. So 1 you can remove, right? Both states are exactly same, then you can remove it. What about D and E. So D is equivalent to E and A is equivalent to C. So one of the state you can remove. So I can cut this off and I can cut this also off. I can cut C as well, I can cut E as well. Okay, and then my state will be reduced. So this is how my reduced diagram will look like. I just I just cut these two rows, C and E. I have cut C as well, I have cut E as well. So I am left with A, B, D, F. So what was A? A was written DB01, B was written ED01, D was written EF01, D was written EF01, and F was there FC00. FC00. But one thing is there. What is that? What is that? Here your states are A, B, D, F. There is no meaning of E and C. E and C are gone. So wherever you see E, in place of that, what you are going to put? D. E can be replaced with D. E can be replaced with D. And A can be replaced with C. So that's the scene. If you cannot have E here, you cannot have C here. You can only have A, B, D, F. So DB is there, DD is there, DF is there, FA is there. So you can only have these four states only. You cannot have E and C. So that I am going to remove with respect to these. Okay. And these are the corresponding outputs. So how will I draw the reduced state diagram? So this I should say reduced state diagram. So here, if you say, if you are currently at state A and applied input is 0, then you will go to the state D. So first I will mark from where to where I am going. I am going from A to D. I am going from A to B. I am going from B to D. I am going from B to D again. I am going from D to D. I am going from D to D. And I am going from D to F. From F to F. And F to A. Now respective input output I will write. So A, if X is 0, I will go to state X is 0, I will go to state D by giving output 0. If X is 1, I will go to state B by giving output 1. With respect to B, if I will go to D only, if applied input is 0, I will give output 0. If applied input is 1, I will give output 1. Okay. If applied input is 0, I will give output 0. If applied input is 1, I will give output 1. What about D? In D, if applied input is 0, I will come back to D and I will give output 0. If applied input is 1, I will go to F and given output will be 1. What about F? If applied input is 0, I will come back to F only and will give the output equals to 0. And if applied input is 1, I will go to A and give the output equals to 0. Okay, is that clear to you? So this is how your reduced state diagram will look like. And that is important because when we see the problems, it will be used. Now we will see the questions of designing FSM. So a particular state table is given, a particular state diagram is given and you need to design the FSM. So how will you design it? So first you will draw the state table. So first task will be draw state table. Draw state table and see if there are any redundant state. If there are any redundant state. Okay, so first draw this table on your own. If I am currently at state A and applied input is 0, then I will be coming back to state A and give the output 0. If I am currently at state A and my applied input is 1, then I will be going to the state B and my output will be 0. So this is how the table will look like. State B. If I am currently at state B and applied input is 0, then I will go to the state 0, then I will go to the state C and giving the output 0. If I am currently at state B and applied input is 1, then I will come back to state B and give the output equals to 1. If I am currently at state C and my applied input is 0, then I will come back to state C and give output equals to 1. If I am currently at state C and my applied input is 1, then I will go to the state A, give the output equals to 1. Is there any redundant state? No, all are same. Sorry, all are different. All states are different. AB 00, CB 01, CA 11. So all states are different. So this is the first task. Now, how many number of states are there? Number of states are 3. Number of states are 3. How many flops you require? If number of states are 3, then how many flops you require? 4, sorry, 2 flip flops required. Flip flops required. That will be 2, right? Are you getting this point? If you remember this thing, 0 to 1, 1 to 3, and 3 to 0. How many states were there? No, here we need to check the biggest one. But if we directly design a down counter or up counter, what we see? The mode number is mode. If I say mode 5 counter, let's forget it. If I say mode 5 counter, then what you will say? That sir, okay, certainly there are 5 states. So if there are 5 states, then you would need at least 3 flip-flops. Right? If there are 5 states, then you would need at least 3 flip-flops. Why is that so? Because to represent 5 states, you need at least 3 flip-flops. Certainly here, if there are 3 states, A, B and C. If I say that I represent A by bit 0 and B by bit 1, so how will I represent C? I can either represent by 0 or 1. So if I represent by 0, then it will be same as A, and if I represent by 1, then it will be same as B. So I cannot represent in 1 bit. I certainly require more than 1 bit. So I require 2 bits. So if I represent this by 0 0, this I can represent by 0 1, and this I can represent by 1 0. Say yes or no? So A I am representing my state A I am representing as 0 0, state B I am representing as 0 1, state C I am representing as 1 0. So a lot of time what happens is that they will write down here 0 0, 0 1 and 1 0. Here only they will write down, and if the examiner is asking, he will tell that which state is represented by what. Or instead of A, he will only write 0 0 only. He will make the diagram in this manner: 0 0, 1 0 and 0 0, and all these arrows, then all these arrows and all these whatever it is. Okay, so he will tell that A is represented by 0 0, B is represented by 0 1, but you should have the aptitude. What is the aptitude you should have? That sir, if there are number of states are 3, final number of states are 3, then I would need at least 2 bits to represent them. So certainly I require 2 flip-flops. For 2 bits I require 2 flip-flops, right? So you need at least 2 flip-flops. So how will the state table look like now? This is how the state table will look like. So I will write down my present state. If my present state is 0 0 and my applied input is 0, or if my present state is 0 0 and applied input is 1. So this I am talking about state A. If my present state is A, then I will come back to state A only if my applied input is 0. So I will come back to state A only if my applied input is 0, and with respect to that I will give output 0. And if my present state is A, which is 0 0 and applied input is 1, then I will go to state B, and my state B is 0 1. I will go to state B, and the respective output I will give, that is 0 only. Are you getting this point? Did you understand this point? If I am at state A, which is 0 0 only, and applied input is 0, then my next state will be A only. My next state will be A, which is 0 0, and the respective output will be 0. Say yes or no? If I am currently at state A, which is 0 0, and my applied input is 1, then I will go to state B, which is 0 1, and respective output will be 0. Say yes or no? Is that clear? Write the same for B and C as well, and then check your answer. So what will be my what will be my B? That will be 0 1, and what will be my C? That would be 1 0. So this represent B and this represent C. So if I am at B and my applied input is, that can be 0 1 0 1, and my applied input is 0, then I will go to state C. State C is represented as 1 0, and give the respective output equals to 0. And if I am at state B and my applied input is 1, then I will come back to state B only, and the respective output will be 1. Say yes or no? If I am at state C and my applied input is 0, if I am at state C and my applied input is 0, then I will come back to C only and will give respective output equals to 0. And if I am at state C and my applied input is 1 0, if I am at state C, sorry, if I am at state C and my applied input is 1, then I will go to state A, which is 0 0, and respective output I will give, that is 1. Say yes or no. So this is how I will represent it. Understood? Okay, let's check back for C. C applied input is 1, then I will go to A, and my respective output will be 1. What will be my D1? So Q1 plus is equals to D1, right? And Q2 plus is equals to D2. D naught, sorry, Q naught plus will be equals to D naught. If in place of D1 D naught, if there was JK, then how would you write it? You have Q1, you have Q1 plus. You know the characteristics table? Right? From the characteristics table, you could write down the value of J1 K1 and J0 K0. Say yes or no? If I was designing using JK flip flop, then how I would design it? Because if I am having JK, J1 K1, J0 K0, with respect to Q1 and Q1 plus, what will be my J1 and K1 value? How do I know that? With respect to Q1 and Q1 plus, what will be my J1 K1 value? How would I know that? I have the characteristics table 0 1 1 0 1 1 0 1 don't care 0 1 don't care. Okay, it would be opposite, sorry, don't care 1 0. So I will see 0 0, then I will write 0 don't care, then I will see 0 again 0 0, I will write 0 don't care, then I will see again 0 1 means 1 don't care. So in that manner I could have write down the value of J1 and K1 as well, right? But here let's write down the value of D1 and D0. So D1 is always equals to Q1 plus and D0 is always equals to Q0 plus. So directly I just need to copy this line 0 0 1 0. Designing with the D flip flop is very easy, okay? But when we design with JK, our number of combination circuits will reduce because there will be a lot of don't cares. So that will be helpful for you because in JK flip flop you get 0 1 don't care in JK flip flop. So that's the thing, that number of combination circuit will be reduced. So when you design, you mostly design with JK flip flop only, not with D flip flop. Like explaining a concept is easier in D flip flop, right? That's why I take the example of D flip flop. If I was designing with JK, then I would write down J1 K1 and J0 K0. Then I would draw the excitation table here, and by matching that excitation table, I had to write all these things. But when you actually design in lab or in industry, there you will design using JK flip flop only. Mostly you will design using JK flip flop because that will reduce the number of combination circuits. And if combinational circuits are less, then your size will also be less. And if your size is less, then power consumption will also be less. But here we are studying by D flip flop. So here you can directly see Q1 plus is equals to D1, Q0 plus is equals to D0. So directly I just need to copy it 0 1. And if your interviewer asks you to design any circuit and he is not telling whether you need to design it using JK or D, so don't be smart there, just design it using D only, okay? If interviewer had asked this question and he asked you to design this, he did not give whether using D, T, JK or SR, so never use SR. That's needless because we will be getting a invalid state. In SR we get an invalid state, so usually we don't use it. Then you can use JK, D, or T. But which is the simplest one? D flip flop. T is also simple, so T also you can use. But better design it with using D or T only. Don't go into JK. If he is saying that design it using JK only, then only you should use JK. Otherwise, you should not. Okay. So this is our D1, this is our D0, and this is our Y. So we will have this combination circuit like this. This will be our memory elements, and then we will be connecting some combination circuits, and we will have our output. So this D will be a function of Q1, Q0 and X. Certainly it cannot be a function of next state, right? There is no meaning of that. It cannot be a function of next state. Next state will depend on this Q and X only. So it cannot be a function of next state. Certainly D2 will be also a function of Q1, Q0 and X. Same goes for Y. It will also be a function of Q1, Q0 and x. Y is a function of q1, q0 and x. Why is that so? Because it is a Millian machine. You can see it is a Millian machine. It is a Millian machine, that's why your y will be a function of applied input as well as the present state. Okay. So let's draw the K map. So for K map, what all will be the minterms here? For D1. For D1. So 0, 1, 2, 3, 4. Plus which all will be the don't care? 6, 7. Why they are don't care? Because 1, 1, 0 and 1, 1, 1, they will never occur. Right? If you are working in this state diagram, then 1, 1, 0 and 1, 1, 1, this condition will never occur. Right? So these will be your don't care. 6, 7 will be your don't care. Here what all are the minterms? 0, 1, 2, 3 and don't cares are 6, 7. What all are the minterms here? 0, 1, 2, 3, 4, 5. 6, 7 are don't care. So you can draw the K map and tell me the reduced expression of D1, D2 and Y. So this is how you will draw the K map. So for D1, 2 and 4, 0, 1, 2, 3, 4 and 6, 7. For D2, 1 and 3. So 0, 1, 2, 3. And for Y, 3 and 5. So 0, 1, 2, 3, 4, 5. Okay. 4, 5, 0, 1, 2, 3, 4. Here we need to check if C, if applied input is 1, 0. Okay. Here you can see output is 1. In case of C, this output is 1 only. Okay. So that error I just got to know. So it would be 3, 4, 5. So in case of C, if my applied input is 1, 0, sorry, if my applied input is 0, in case of C, if I am at state C, if my applied input is 0, then I will go to the state C again to 1, 0 only by giving the output equals to 1, by giving the output equals to 1. So this is how it will look like. Okay. So 3, 4, 5, 6, 7. Right. So let's see the reduced expressions. So here you can see this will be one of the pair and this will be the other pair. So what will be your D1? So D1 here in this loop, what is constant? Q0 x bar. And in this pair, what is constant? Q1 is certainly constant. Along with that, x bar is constant. Right? So it is Q0 plus Q1 x bar. Here only this pair is there. Directly you can see this pair is there. So what will be your D0? Here I am writing D2. D2 is actually D0 only. Okay, this error I again and again do it. D1, D2, D1, D0 we should write. So what will be my D0? So D0 Q1, here Q1 bar is constant and x is constant. Q1 bar x. And what about y? 1 I get this, which is Q1 only, plus other one I get this, which is Q0 x. Okay. So these are my expressions. Q1 plus Q0 x, Q0 plus Q1 x bar and Q1 bar x. So this you should have done on your own only, right? And this is how you design it. You can see what is your, I will make 2 flip-flops. All should be clocked, both should be clocked. Both should be clocked. So what will be your D1? D1 will be Q1 plus Q0 dot x bar. So it is Q1 plus Q0 dot x bar. What will be your D0? D0 will be Q1 bar dot x. This will be your D0. And what about your y? Y is Q1, this is your Q1 plus Q0 into x, Q0 into x. So this will be your y. Okay. So this is how you design your FSM. Now some gate guys can say that, those who are preparing for gate, they can say that, sir, why it is necessary, why it is necessary to design in this manner, why it is necessary to study this, because in gate examination there is very rare chance that they can ask the designing part. But what they can do, they can make this as a black box and they can ask you what should come here. Okay, these kind of questions they can ask, or they can ask you to analyze this. So you can also analyze it by writing the present state and then the output. We will see the example how to analyze a given FSM. So that also we will see, but directly from here also, if you can design, then certainly you can analyze as well. If you can design an FSM, then certainly there is no need to worry that you will certainly be able to analyze it as well. Okay. Now you will solve this question. So first what you need to do, you need to draw the state table and see if there are any redundant state. So draw state table. Check redundancy. Okay, draw the state table and check redundancy, then see how many states are there and how many flops you will be requiring, and based on that you make the state table and now design it. So I will pause the video, you will also pause the video and do it on your own. I will put the charger on and drink some water, and then we will start analyzing this particular state diagram. Okay then, so do it on your own first. Okay, so I hope you must have done it on your own. So let's check it. First we will draw the state table and we will check if there is any redundant states or not. So let's draw the state table. So these are the present state A, B, C, D, E, F, A, B, C, D, E. These could be my present state. If I apply input x equals to 0, then my next state will be A only. So if these are the states, then I can write down the present output directly. If these are my state A, B, C, D, then my present outputs will be, if I am at state A, 0. If I am at state B, output will be 1. If I am state C, output will be 1. If I am state D, output will be 0. If I am at state E, output will be 0. Okay. So if I am at state A and my applied input is 0, then my next state will be A only. If I am at state A and applied input is 1, then my next state will be B. If I am at state B and my applied input is 0, then my next state will be C. And if applied input is 1, next state will be E. If I am at state C, applied input is 0, then next state will be E. And applied input is 1, next state will be D. If I am at state D, applied input is 1, then my next state will be D only, and if applied input is 0, then I will go to E. And if I am at state E, applied input is 0, then I will go to state A, and if applied input is 1, I will go to state D. So what you can see here, D is equivalent to E. So this I can ignore. So E will be cancelled. So A, B, C, D, only 4 states I am having, and this is how my diagram will look like. A, B, C, D, A to A, B, C, E, E, D. A, B, C, E, E, D and A, D and A, D. And these are the outputs 0, 1, 1, 0. Okay. So number of states are 4. Reduced total state. So these are 4 only. And number of flip-flops required to represent 4 states, which are A, B, C, D. So you cannot represent it by 2 bits, but certainly by using 3 bits I can represent it. 0, 0, 0, 1, 1, 1. Okay. So number of flip-flops required are 2. So present state will be Q1, Q0, and input will be X, that will be 0, 1, and your next state you can write, then you can write down your output and you can write down your D1, D0 value. So try doing it on your own. So this is how I will write it. If my present state is 0, 0, that is my A, and applied input is 0, then my next state will be A only, and my output will be what? 0. So output will be, in case of A, my output will be 0, 0, and in case of B, my output will be 1. In case of C, my output will always be 1, and in case of D, my output will always be 0. This you can see here. And with respect to the applied input, that is 0 and 1. So if my present state is 0, 0, applied input is 1, then my next state will be 0, 1. My next state 0, 0, my next state will be 0, 1. If my applied input is 1 and my given output will be 0. If I am currently at 0, 1, any example you can take. Here you can see. If I am currently at state B and my applied input is 1, then my next state will be D. B, applied input is 1, then my next state will be D. So D and E are equivalent, so this should be replaced with D. And my output will be 1. So that's how I have written it. So I hope you must have also written it. And what is your D? D1? D1 is simply Q1 plus. D1 is simply Q1 plus. And D naught is simply Q naught plus. Okay. So directly you can write 0, 0, 1, 1, 1, 1, 0, 1. Here you can write 0, 1, 0, 1, 1, 1, 0, 1. I hope that you are fine with writing this table. Okay, this is very easy. Let's take another example to make you feel better. So this example we are taking. If I am going, where I will go from D to A, I will go if my applied input is D to A, I will go if my applied input is 0. If my applied input is 0. If my applied input is 0. And if I am at A, if I am at D, then my output will certainly be equals to 0 only. And if you are at A, then output will be 0. So this kind of diagram should be there. D to A with applied input 0. So if you are going from D to A, applied input is 0 and output will be 0. Okay, so this is how you write it down. Okay, so this table you can design on your own. Now your D1 will be a function of what? Q1, Q0 and X. D0 will be a function of what? Q1, Q0 and X. What your Y will be a function of? Your Y will be a function of, you can say that it will be a function of Q1, Q0 and X, because you will draw the K-map there. But we know it is a Mealy machine. It is what? Sorry, it is a Moore machine. You can see it is a Moore machine. It is a Moore machine. This is what? It is a Moore machine. So if it is a Moore machine, then certainly this function will be different. So certainly my function will be, Y will be a function of only Q1 and Q0. And when you draw the K-map, you will realize that Y is only a function of Q1, Q0 only. When you draw the K-map. Okay, so try drawing the K-map. So this is how you will draw the K-map. You can see the minterms. So let's write down the minterms here. D1 has the minterms of 0, 1, 2, 3, 4, 5. 2, 3, 4, 5. D2 has a minterm of 0, 1, 2, 3, 4, 5, 6, 7. And Y has a minterm of 0, 1, 2, 3, 4, 5. So Y 0, 1, 2, 3, 4, 5. What about D2? 1, 3, 4, 5, 7. 1, 2, 3, 4, 5, 6, 7. Okay. And what about D1? 2, 3, 4, 5. So 0, 1, 2, 3, 4, 5. 2, 3, 4, 5. 0, 1, 2, 3, 4, 5, 6, 7 as well. 7 is also there. 6, 7. So 1, 2, 3, 4, 5, 6, 7. Okay. So let's see what pairs you are getting. So here I see 3 pairs are there. 1. Is there any quad? Do you see any quad? No. So 3 pairs are there. You will have to write down everything. So D1 is what? D1 is Q1 bar into Q0 plus Q1 into, here what is constant? Q0 bar plus Q1 into X. Q1 XOR Q0 plus Q1X. What about D2? So here I can see there is a quad. So this is at D2. So here only what is constant? X is constant. Right? Here only X is constant. Plus what else is constant here? This is a quad. So here Q1 is constant and Q0 bar is constant. Q1 is constant and Q0 bar is constant. What about this? This and this. So what about Y? Q1 bar is constant and Q naught is constant, plus here Q1 is constant and Q naught bar is constant. So Q naught XOR Q1. So these are the expressions. This is the expression, this is the expression, and this is the expression. So you can design the circuit on your own now. Okay, finding the expression was the important task. Designing is not that difficult, or nothing is difficult actually. So you can design it on your own. How you will do? This flow you will be having, this flow you will be having, and then Q1 XOR Q naught you will do. Q1 XOR Q naught you will do. Then at one place you will do Q1 and X, sorry, Q1 dot X you will do, and then both of the outputs you will take, and after that you will do the addition. You will take the OR gate and then you will feed back to the D1 input. So this is how you are going to design it. You can design it on your own. It is not that difficult, right? So try designing it on your own. There is no circuitry available because I haven't drawn it. That is very easy. And like after that, no one will ask you actually. Okay, even in the interview, they will ask only these expressions D1, D naught and Y. If you are able to write down the expression, then you can design it. That's very simple, right? Only designing part is not that difficult here, right? Yeah, so now we will see a very small topic, which is drawing state diagram of standard flip-flops. So it has nothing to do with FSM. Okay, it has nothing to do with FSM. In FSM, most of the concept we have already seen, and there will be some concept named sequence generation and sequence detection. Sequence generation and sequence detection. That is also related to FSM only. So that we are going to see in the next video, and after that we will solve a lot of problems. So it will be all clear to you. Your FSM will be all clear to you. In the next video, you will study about sequence generation and detection, overlapping, no overlapping, everything you will see. And after that, you will see what you will see after that. After that, you will see some questions. So combining all these three videos, your concepts will be much clear in this particular topic. So that we will see in the next video. But before that, let's see a simple topic. It has nothing to do with FSM, but it is important. Not important, I would say you should know it. Okay. So you need to draw the state diagram of some standard flip-flop. This is the SR flip-flop. We will study about JK and D and T as well. So in SR flip-flop, these are the S and R are the inputs, and you receive some output there. Q will be your output. Okay. And this is the table. What do we call it? Excitation table. This is the excitation table. So with respect to 0, 0, 0, 1, 1, 0, 1, 1, what all are your SR inputs? 0, 1, 0, don't care, 0, 1, 0, don't care, 0, 1, 0. So if you are currently at state 0, this is your current state. What I can do is that I can denote S0 by state 0 and S1 by state 1. This I can do, or I can directly say that my current state is 0, then my next state will also be 0. From 0 to 0 I will go if my applied input is 0, don't care. Say yes or no. Now, if my current state is 0, I will go to state 1. I will go to state 1. From 0 to 1 I will go if my applied input is 1, 0. I will go from, if my current state is 0, I will go to state 1 if my applied input is 1, 0. If my current state is 1, I will go to state 0. If my current state is 1, I will go to state 0 if my applied input is 0, 1. And if my current state is 1, I will come back to state 1 only if my applied input is, don't care, 0. That's it. So this kind of questions can come directly. They can say that draw state diagram of SR flip-flop. Then you should not be confused that what he is asking. Directly write down the state table, or you should say excitation table. You can write down. Then you can directly tell him that, sir, I will go from 0 to 0 if my applied input is 0, don't care. I will go from 0 to 1 if my applied input is 1, 0. I will go from 1 to 0 if my applied input is 0, 1, and I will come from 1 to 1 if my applied input is, don't care, 0. That's it. Why it is not an FSM? In FSM, there is a certain output logic as well, no? Like there should be some output logic connected here. These kind of output logic should also be there. So there is no different output. The state diagram looks like that there is something different, but there is nothing different. It is very simple. Okay, do it on your own for JK flip-flop. So you will go from state 0 to 0, 0 to 0, if your applied input is 0, don't care. You will go from 0 to 1 if your applied input is 1, don't care. You will go from 1 to 0 if your applied input is don't care 1, and you will go from 1 to 1 if your applied input is don't care 0. Same goes for D as well. You will go from 0 to 0 if your applied input is 0. You will go from 0 to 1. This excitation table you can directly write it 0 0 0 1 1 0 1 1, and q1 plus is equals to D, so 0 1 0 1. So 0 to 0 applied input is 0, 0 to 1 applied input is 1, 1 to 0 applied input is 0, and 1 to 1 applied input is 1. Okay, this is the applied input, this is the input I am writing, and these are the state 1 to 1 applied input is 1. Okay, do it for T flip flop 0 to 0, and this should be T, not D. 0 to 0 if applied input is 0, 0 to 1 if applied input is 1, 1 to 0 if applied input is 1, and 1 to 1 if applied input is 0. That's it. Okay, so these are the state diagram of standard flip flops. So that was not important I would say, but that was necessary, because sometimes in the gate as well these kind of questions can come, and in your interview as well these kind of questions can be asked. So it is very simple, but if it is not taught then you might get confused, but now it is all clear. Okay, so in the next video we are going to study about sequence generation and detection. After that we will solve a lot of problems, and it will clear all the concepts which are required. Okay then, so let's meet you in the next video. Hi everyone, so now we are going to study about our next topic, that is sequence generation and detection. So first we will study about sequence generation. We will generate a particular sequence, and then we will see how to generate a particular sequence. So sequence generation is a very simple topic, but sequence detection is a bit typical, and also it is very important as well, and we will see the complete depth. And once you watch this particular video, after that there will be no confusion in sequence generation as well as in detection. First let's start with sequence generation. So what you need to do, you need to design a circuit, such that it generates this particular sequence, which is 1 1 1 0, then again 1 1 1 0, then again 1 1 1 0. So this sequence you need to generate. So what does that mean? That if first clock pulse come, if the first clock cycle is coming, then 1 should come. Then another clock cycle is coming, then another 1 should come. Then another clock cycle is coming, another 1 should come. Then another clock cycle is coming, 0 should come. Then another clock cycle is coming, 1 should come. Clock cycle 1, clock cycle 1, clock cycle 0. So in that manner it should go. So this one and this one, these are different. This one and this one, these are different. This one and this one, these are different. Certainly 0 is different from 1, that's for sure. Are you getting my point? With every clock cycle 1, then again 1, then again clock cycle again 1, then again clock cycle, then 0. So these ones are different. These should be denoted differently. So if I say, let's just say 1 is already different than 0. So if I say that if I introduce another bit, that is 0, and then I introduce another bit 1 in front of this. So now this one and this one are different, right? It is 1 1 and it is 0 1. But how will I differentiate this one? Either I will have to connect a bit 0, or I will have to connect a bit 1. So if I connect a bit 0 here, then these two are same. So that's an issue for me. And if I connect bit 1, then these two are same. So that's an issue for me. So using only one bit I cannot do it. But if I use 2 bits, then what I can do? If I use 2 bits, I can give 0 0 to this one, 0 1 to this one, 1 0 to this one, and 0 0 to this one. Now all 0 0 to this one, I can give anything. 0 0 I can give here, 1 1 I can give here, 1 0 I can give here. Here also I can give anything. I can give 0 1 to this one, 1 0 to this one, 1 1 to this one, or anything else. Basically I need to differentiate all these 4 bits. So 1 1 1 0. Now all these are different. All 4 different. Now what has your question become? Now your question has become that you need to generate a sequential circuit which will go from 00001 to 011, then to 101, and then to 000, and then again back to 001. And here at the last bit, I will collect my output. So at the last bit I will collect my output. We will see the design, it will be more clear to you. So what did I do? I needed to generate this sequence 1110. Then I got to know that my 1 is being repeated 3 times. So to differentiate that, I would need another 2 bits 000110, and for 0 I can connect anything. So this is the state diagram I am getting. Here there are 3 bits, that means I would require 3 flip-flops. 3 flip-flops required. So using D flip-flop I can design it. This counter I am going to design. This particular counter I will design, and across this bit, if I call this as Q2, this as Q1, and this as Q0. So across Q0 I will collect my final output. So first I will see 1 1 1 0, then again 1 1 1 0. Are you getting this point? We will design it, let's see. So now what has your question become? You need to design a counter which follows this sequence from 001 to 010, 101 to 000. So this is how I am gonna design. I am designing a synchronous counter. This is my synchronous counter. So I told you I have given the complete method how to design a synchronous counter, and we have seen a lot of examples as well. How do we design a synchronous counter? First we write down all the possible combination. So from 0 to I am going to 001. From 001 to I am going to 011. Then from 011 to I am going to 101. And from 101 to I am going to 000. And rest all these are don't care. So these conditions will not even occur. So these conditions are don't care. And what is D2? D2 is simply Q2 plus. What is D1? D1 is simply Q1 plus. And what is D0? D0 is simply Q0 plus. So these are don't cares. Right? Now my D2 will be function of Q2, Q1 and Q0. Same goes for D1, that will also be a function of Q2, Q1 and Q0. And same goes for D0, that will also be a function of Q2, Q1 and Q0. And if we write down the minterms, what are the minterms for D2? Minterms for D2 are 0, 1, 2, 3 plus don't care 0, 1, 2, 3, 4, 5, 6, 7. So don't care are 2, 4, 6, 7. What about D1? D1 has a minterm of 1 and don't cares are 2, 4, 6, 7. What about D0? D0 has a minterm of 0, 1, 0, 1, 2, 3 and minterms are 2, 4, 6, 7. Right? So I can make the K-map now. This is how I will make the K-map. Okay, and from there I can get the value of D1, D2, D1 and D0. So what is the value of D2? So here I can see a quad. So this process we have already studied, that's why we are moving a bit fast here. So this is a quad. What is constant here? Only Q1. Again saying I am having elaichi so that I do not cough. I am not a fan of Ajay Devgan. Okay. Again and again I am repeating it so that no one comments, sir, are you a fan of Ajay Devgan because pan masala? No pan masala. I don't eat these kind of things. Just I am having the elaichi. If you have the elaichi in your mouth, you will never cough will never come. So that I can explain the things better, right? So what about D0? D0 is Q2 bar only, right? D0 is Q2 bar. So this is your D2, D1 and D0. So D2, D1 and D0. Okay. Now the thing is, you will design this particular circuit. This is the circuit, and here you will collect your output. This is your final output. Because what we wanted this sequence 1 1 1 0, and this is what you are going to get 1 1 1 0. But The thing is, you need to check whether it is going from lockout problem or not. Whenever we design a synchronous counter, we see what will happen to these states, whether it is going into lockout or not. So if it is going into lockout, then that will be a problem for us, because here we have assumed that it will be starting from 0 0 0 0. But what if it starts from 0 1 0? Where it will go? So since I am done designing this, now I will see whether I am suffering from lockout problem or not. So what will be my Q2 plus? Q2 plus will be equals to D2, and D2 is equals to Q1. What will be my Q1 plus? Q1 plus will be equals to D1, and D1 is equals to Q2 bar, Q1 bar into Q naught. And what about Q naught plus? That will be equals to D naught, and that is equals to Q2 bar. So Q2 plus is equals to Q1. So 1 0 1 1. Q1 plus is equals to Q2 bar Q1 bar into Q naught. So this is 0, this is also 0, this is also 0, and this is also 0. All these are 0. And Q naught plus is Q2 bar. So 1 0 0 0. So let's write it as 2. So from 2 to you are going to 5. What was the cycle? Here what was the cycle? I designed for 1 3 5 0. So what I designed? 1 3 5 0. 1 to 3, 3 to 5, and 5 to 0, and then came back to 1. This is what I designed. Now let's check. From 2 to 5 you are going. So 2 to 5 you are going. No issue here. 4 to 0 you are going. No issue here as well. 4 to 0 you are going. Here 6 to 4 you are going. 6 to 4. 6 to 4 you are going. Again no issue. 6 to 4, then 4 to 0, again no issue. Then 7 to 4 you are going. 7 to 4 you are going. So 7 to 4 you will go, 4 to 0 you will go. So there is no another loop. There is only one loop. So there is no lockout. So the design is perfect. Design is perfect. So even if in the worst case, if it starts from 6, then after one clock cycle it will go to 4. Basically, if it starts from 1 1 0, so first you will receive 0 output, then you will receive again 0 output. After that you will receive again 0 output, and after that you will have the corrected output. That means 0 0 1 0 1 1 and 1 0 0. This is what you are expecting. Then again 0 0 0, then 0 1 1. What we wanted? Triple 1 0, right? We wanted triple 1 0. So that you will be getting triple 1 0. So 5 is 0 1 0 1 actually. 5 is 1 0 1 and then 0 0 0. So the triple 1 0 you will be getting. You will be working in this loop only. You will keep on working in this loop even if you are starting from 6, 7, 4 or 2. Eventually you are going to fall in this loop only, and if you collect your output here, you will receive 1 1 1 0, again 1 1 1 0, and in that manner it will keep on going. Okay. So this is what this is how we can design it. So this was our first way of designing. But here what is the issue? You can already see, if you are designing a synchronous counter, there is very high chance that lockout problem may occur. So once your designing part is done, then after that you check that if there is a lockout problem or not. And when you find there is a lockout problem, you redesign it. So that is an issue for us. So that's also a good design. That's also one of the option. But there are other methods as well. So let's see method 2. So in method 2, I will be using asynchronous counter. So what I will be doing? So here you are not going to understand anything. Okay. So what I need to design? 1 1 0. This I need to design. Okay. Now let's just say I have a up counter of 2 bits. So let's just say it's starting from 0 0. So then it will go to 0 1, then it will go to 1 0, and then it will go to 1 1. Now what I can do? This is the up counter. There will be 2-bit output, 0 0 0 1 1 0 1 1. So whenever you get 0 0 output, I will design a combination circuit here. And this will be my final output. So whenever I get 0 0 here, this should give me 1. Whenever I get 0 1 here, this should give me 1. Whenever I get 1 0 here, this should give me 1. And whenever I get 1 1 here, this should give me 0. Then again 0 0 would come, 1 1 1 0. So here what I will be having? 1 1 1 0, again 1 1 1 0, again 1 1 1 0. Is that a good idea? If you did not understand it, you will understand it certainly. Okay, no need to worry about that. So let's see the example. So same example we are taking, design a pulse train generator. So what I'm going to do, I will design a up counter which gives me the following output. So this I am calling as Q1 and Q0. So my up counter will give me 0 0 0 1 1 0 1 1. Now at the output of up counter, I will be using another sequential another combination circuit which will give me for 0 0 it will give me 1, for 0 1 it will give me 1, for 1 0 it will give me 1, and for 1 1 it will give me 0. So this I will be using. Okay, so then with respect to these outputs I will design a combination circuit which give me outputs respectively 1 1 1 0. So what will be my f? My f is simply q1 bar plus q0 bar, or you can say q1 q0 bar. F is q, you can write the max terms which is q1 bar plus q0 bar, so q1 q0 bar. So simple, what is this? This is your up counter, and here I am collecting my final output. So what will happen? First 0 0 will come, output will be 1. Then 0 1 will come, output will be 1. Then 1 0 will come. Here it is q1 into q0 bar, q1 into q0 bar. Then 1 0 will come, output will be 1, and then 1 1 will come, output will be 0. Then again the cycle will keep on going. Again 0 0 will come, output will be 1. Again 0 1 will come, output will be 1. Again 1 0 will come, output will be 1. Again 1 1 will come, output will be 0. So this cycle will keep on going, and at the receiver you will have 1 1 1 0 1 1 1 0 1 1 1 0 1 1 1 0 in that manner only. Are you getting this point or not? So that's the way it will go. So this is also a good idea, but here we were lucky, we did not have to use any clear or preset input. But what if this example is given? Try it on your own, you will understand what is the catch here. You need to generate this sequence 1 1 0 1 1. This sequence you need to generate. First tell me how many flip-flops will be required. Look, here there is no concept that you need to differentiate these stages, that I need to differentiate this guy and this guy. There is no concept like that. Why is that so? Because each states are different. Each states are different. With respect to one stage, I am getting one output. With respect to other stage, I am getting another output. Basically, what do I mean is that if I design an up counter, which is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So with respect to this I will be getting 1, with respect to this I will get 1, then I will get 0, then I will get 1, then I will get another 1. So this is what I need. If this stage comes, what I am going to do? I am going to clear it. Say yes or no. Here I will clear it. This I don't want. So I want my output to go from 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0. Just as I get 1 0 1, output should be cleared. Are you getting this point? So number of bits in the sequence are 5. That means at least 5 you need, at least 5 combination you need where you can assign the output. At least 5 combination I need. The number of bits in the sequence are 5. If the number of bits were 4, here number of bits were 4. So I thought that at only 4 sequence I need. And if I need only 4 combination, I need, and to each combination I can assign a value. So using only 4 combination I can assign these values. But now I have number of bits equals to 5, which are 1 1 0 1 1. So I need at least 5 combination to whom I can assign the value. At least I need 5 combination. So for using 5 combination, for getting 5 combination, how many bits do you require? 3 bits. And 3 bits means 3 flip-flop. Did you understand this point or not? I am designing it using asynchronous up counter. Okay. Number of bits in the sequence are 5. So what do I know? That each bit I will be assigning to a particular combination. I will be assigning 1 to a particular combination, then again 1 to another particular combination, then again 0 to another particular combination, then again 1 to another particular combination, and then again 1 to another particular combination. So I need at least 5 combination. And if I need at least 5 combination, then from 2 bits I can get only 4 combination, but from 3 bits I can get 5 combination. Usually there are a lot of formulas which are taught in this particular method, but we are not covering any formula here. We will not see any formula. We will think, okay, you are designing it using asynchronous counter. That means you are either designing up counter or down counter. Then you will use a clear input. Also, you know one thing, that is that if I am designing it using up counter or down counter, that means each combination is getting a particular output. 0 0 0 1, 0 1 1 1, 0 1 0 0, 0 1 1 1, 1 0 0 1. That means I need at least 5 combination. If I need 5 combination, that means required flip flops are 3. Okay, well and good. I hope this is clear to you. So what I am going to write? Q2, Q1 and Q0. With respect to that, I will have my output F. So these combination I can write. Okay, so if 0 0 comes 1, 0 0 1 comes 1, 1 0 0 1 0 comes 0, 0 1 1 comes 1, 1 0 0 comes 1. After that, what should be your F? F I am saying. There is a up counter, okay, 0 0 is coming, F should be 1. Basically this is the scene, that there are 3 output bits. This is your combination circuit, this is your up counter. So 0 0 is coming, 0 0 0 is coming, output should be 1. 0 1 0 is coming, output should be 1. 0 1 0 is coming, output should be 0. 0 1 1 is coming, output should be 1. 1 0 0 is coming, output should be 1. But in this up counter, I will use a clear input, which will make sure that these conditions do not even occur. Say yes or no. This clear input will make sure that these conditions do not even occur. Why is that so? Because let's just say if 101 is occurring, this 101 is occurring. So after 1 clock cycle, 101 will occur. And I do not even want this. I do not even want 101 to occur, because I want this sequence to be repeated. 11011, then again I want to go back here. Say yes or no. Right, so this is the sequence I want. So I make sure that these conditions do not even occur. So all these will be don't care. What will be my clear input? Here I am going to break it, right? This here I am going to break it. So this condition I do not want. What I don't want? Q2, Q1 and Q0. 1 0 1. So there I told you a trick, and I also told you when that particular trick will be applicable. When it will be applicable, you are designing an up counter. Okay, where you are starting from? If you are designing up counter, that means you are supposed to start right from the 0. Are you starting from 0? Yes, I am starting from 0. That means trick is applicable. Now, if you are designing up counter, up means you are high in your life. If you are high in your life, that means you will only look at 1. So if I am only looking at 1, so I need to design clear input. So what I will write? Q2 into Q0, and Q2 into Q0, 1 into 1. I want my clear input to be high. So 1 into 1 is 1 only. So my clear input is high. So this is the ideal design of clear input. What is the ideal design of clear input? This is the ideal design of clear input, which is Q2 into Q0. Say yes or no. Right? So this is my clear input. I hope you already know this thing, because we have already studied this in a very in-depth manner. We spent around 2.5 hours just to understand this particular concept. When this trick is applicable, when this trick is not applicable, that we have seen in very in-depth manner, right? What about F input? Do you need to make a K-map here? What do you think? What about F? Do you need to make a K-map? No. What do I do is that all these don't squares are there. I can consider all these as 1. If I consider all these as 1, then I will be left with only one max term, that is 0 1 0. So I can write my F is Q2 plus Q1 bar plus Q0. There you Q2 plus Q1 bar plus Q0. This is your final output F. Okay. So this I will be removing. So you should have a good aptitude that 11011 is there. These are don't care. I can assume any value. If I assume one value here, I will be left with only one max term. So that will be Q2 bar, sorry, Q2 plus Q1 bar plus Q naught. So that will be my F, and this will be my clear input. So this is how I will be designing it. You can see this is the clear input. What is the clear input? Q naught into Q2. So Q naught into Q2 is fed as the clear. So how do we design it? That also you know by the trick, and trick is applicable if you are starting right from the 0. And if you are designing up counter, that means you will be focusing on 1 only. So if I focus on 1, Q2 into Q naught is giving me 1. So that's it. So this is my clear input. Okay, this is my clear input. And what about this final F? This will be my output, final output F. So my final output is Q naught plus Q1 bar. From here Q1 bar would be coming, and from here Q2 is coming. So here I will receive my final output. So if first clock cycle comes, here you will have 0 0 0. So what you are going to have? 1. Then you will have 0 0 0 1, again 1. Then you will have 0 1 0, then you 0, then again 1, then again 1, then again this cycle will come here. So this is how you can design. Okay, so this was the method 2. The third method is using shift register. So that we have already seen with the help of an example when we were studying shift register. Okay, you can see the example. So this much knowledge is more than enough for gate aspirants. They can give this particular circuit and ask you the output, that which sequence it will generate. For gate aspirant, they will give this particular circuit and they will ask you what will be the sequence generated. So you can directly see that, okay sir, this is a down counter. Actually it is a down counter, but I need to make it up counter, so I will use this. Also I can use this here as well. Okay, so now it is up counter. In the previous design, did I make it up counter or down counter? Okay, it was up counter only. So here also we are using up counter only, so I should make it up counter. So this is a up counter. You will get to know that it will start from 0 0 0, it will keep on going. Then you will see where it is being cleared. Okay, it is cleared at 1 0 1. So if it is being cleared at 1 0 1, that means it is being cleared at 1 0 1. Yeah, right. It is being cleared at 1 0 1. So that means that will not occur. So it will count from 0 to 4 only. If it is counting from 0 to 4, so what will be your output? 1 1 0 1 1. Then it will keep on going. So if you can design, then certainly you can analyze that well. Right? You can certainly analyze this particular circuit. Right? So that's it about our sequence generation. Very easy topic, very straightforward topic. Let's see some common gate question which has been asked. So the minimum number of JK flip-flops required to construct a synchronous counter with the count sequence 0 0 1 1 2 2 3 3 and then 0 0. So 0 0. So in that manner they asked 0 0 1 1 2 2 3 3. So how would you show 0 at 0 only? How would you show 1 at 1 only? How would you show 2 in binary? That would be 1 0 1 0, and this would be 1 1. This would be 1 1. Now you need to differentiate this 0 and this 0, this one and this one. Look, 0 and 1 are already different. You do not need to differentiate it, but both 0 0 are same. You need to differentiate it, and we are using synchronous counter. So we are using first design. So this is the design we are using. This design we are using. In synchronous counter, we need to differentiate everything, right? We need to differentiate all, and then we design a counter, and with respect to that we get our output. So if we are using synchronous counter, then we need to differentiate everything. Okay, so 0 and 0 both should be differentiated from each other. How I can differentiate it? Using one bit only, 0 and 1. Can I differentiate these two as well? Yes, using one bit only, 0 and 1. Then these two also should be differentiated, 0 and 1. These two also should be differentiated, 0 and 1. But here you are using 3 bits, so here also you need to use 3 bits only, no? Are you getting this point? If I am using 3 bits here, so here also I will use 3 bits. So what I should do is that first I should denote 0 0 and 1 in 2 bits. Then I need to differentiate. So this I will put 0 1, this I will put 0 1. Basically here 1 is repeated twice, 0 is repeated twice, 2 is repeated twice, and 3 is repeated twice. So differentiate two 2 times. What I can do? I can add a bit 0, I can add a bit 1. So both are different now. So using only 3 bits, how many bits are required? 3 bits required. That means 3 flip-flops are required. That's it. Okay. Solve the next question on your own. 0, 1, 0, 2, 3. 0, 1, 0, 2, 0, 3. So for 3 you would require 2 bits, that I know. So certainly I will denote all the numbers in 2 bits only. So this and this are already different, this is also already different, this is already different. What is the scene? Scene here is this 0, 0. So these I need to differentiate. These I need to differentiate 0, 0, 0, 0 and 0, 0. Can I differentiate it using 1 bit only? If I connect a 0 here, this would be 1, and again I need to connect either 0 or 1. If I connect 0, this would be same, and if I connect 1, then this would be same. So using 1 bit only I cannot do it. So I need to use 2 bits. So if I use 2 bits, that means this will be 0, 0, this will be 0, 1, and this would be given 1, 0. You can give anything to these. 0, 0 you can give, 0, 0 here also you can give, 0, 0 also here you can give. So how many bits you need to use? 4 bits. And what does that represent? 4 flip-flop. So what is the answer? 4 flip-flop. If the question was in this manner, okay, try answering on your own. How many flops you will be requiring? What do you think? So it is 0. For 3 you would require 2 bits, so 0, 0, then 0, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, and that is 3, 1, 1. So you need to differentiate between these 2 and these 4. So what do you think what you will do? You need to differentiate 4. If you need to differentiate 4, then at least you require 2 bits 0, 0, 0, 1, 1, 0, 1, 1. So all 4 are differentiated. Anything you can give here. Now what about this? If I give 0, 0 here, at least I need to give 0, 1. Apart from 0, 0, I can give anything. And here also I can give 0, 0. So how many flops you require? 4. Directly you can see that it is coming for 4 times. If it is coming for 4 times, then at least I would be requiring 2 bits to differentiate these 4. It is coming 2 times. Then at least I would require 1 bit. But here I would require 2 bits. So 2 bits for this and 2 bits to represent 3. So 2 plus 2, 4 bits you require. So answer will be 4 flip-flop. I hope you are understanding it. To represent the numbers, I need 2 bits. Because if I am getting state 3, then at least 2 flip-flops has to be there. From only 1 flip-flop you can get 0 and 1 only. So if I need state 3, then at least 2 flip-flops has to be there. So if 2 flip-flops are there, okay, it is fine. Now you need to differentiate 1, 1, 1, 1. So 2 bits, 2 bits, 2 bits, 2 bits. All these are done using synchronous counter. All these are done using synchronous counter. So that's the scene. In synchronous counter, what do? We generate the states and then we design the counter. But using asynchronous, what is the scene? Using asynchronous, the scene is, let's just say you need to generate this pulse using asynchronous. So what you will see, there are 4 bits in the sequence. So if there are 4 bits in the sequence, if I take any up counter or down counter, so with respect to each combination, I will assign a particular bit. So if there are 4 bits in the sequence, that means I need to take 4 combination. So for 4 combination, what I will be requiring? 2 flip-flop. In this case, I require 5 combination. For 5 combination, I will be requiring 3 flip-flops. There you go. Okay, so that's how you will be solving it, right? So that's it. Very easy questions are asked in the GATE examination. Even in the interview, they will not focus much on this. They can just ask a simple question and generate this particular sequence. They will not even ask whether using synchronous counter or asynchronous counter. They will just ask, you need to generate this particular sequence. Will you be able to generate it? Yes, certainly you will be able to generate it. And if I had been the student, I will be using asynchronous counter because that is a much easier design. The only thing is here you will have to design the clear input. So if I need to design a clear input, so that also I can do quickly because I have the trick. So I will start right from the 0 and by using the trick, I will design this clear input as well and F is already visual. Okay, so better I will be designing with this method rather than going for synchronous counter. Okay, synchronous counter also I can take, but that may take some time. But here Also in synchronous counter, the problem of lockout can also occur. So better I will be designing in this method. Okay. So that's it about our what do we say, sequence generation. Now we are going to study about sequence detection. Okay. So now we need to detect a particular sequence. So let's just say this is my particular input 110 110 110 110 11. This is the input, and you are giving this input to a sequence detector which detects the following sequence 110 11. So what output you will receive? So output will be of two types. One will be when overlapping is not allowed, and one will be when overlapping is allowed. So let's see the example, you will understand more. Okay. So this is the input applied. Okay. Here you can see you need to detect the sequence 11011, and overlapping is not allowed here. Overlapping is not allowed. So what will happen? First this one will come. You need to generate this sequence 11011 11011. So output will be 0. Then 11 will come. Again output will be 0. Then 110 will come. Sequence will keep on coming. Then again output will 0. Then 1101 will come. Again output will be 0. Then 11011 will come. Okay. Now output will be 1 because this sequence has been generated. Now what the question is saying, overlapping not allowed. Overlapping not allowed means just as this has been generated, your register will be clear. All these value will be clear. Now nothing is there. 110 has been generated, nothing is there. Now next 0 will come here. Directly 0 is come. 0 is coming. These are gone. So output will be 0. Then 1 will come. Output will again be 0. Then 1 1 will come. Output will again be 0. Then 0 1 1 0 will come. Output will again be 0. What do you need to generate? 1 1 0 1 1. Then 0 1 1 0 1 will come. So 1 1 0 1 1 you need to generate. So output will again be 0. Now how many bits are there? 5. And this detector detects 11011. This detector which we are designing, it is detecting 11011. So that means there are 5 bits, right? So in the register as well there has to be 5 bits only. So in the next cycle what will happen? 0 1 1 0 1 and then another 1 will come, but it will clear this. Okay, in the register there can be only 5 bits. Are you getting this point? If it is detecting 5 bits only, so in the register as well, in the register you can have only 5 bits. So here 11011 is coming, so that means yes, it is detected. So you will receive this output. Okay. So when you feel like that there are being 6 bits in the register, then you need to eradicate one. Okay. So now just as it has been detected, so it will be all clear. Then 0 will come, again 0. After that 0 1 will come, again 0. Then again 0 1 1 will come, so again 0. So that's the output you are receiving. Okay. So this is the output you will receive. Well and good. So first 0, then 1, then 0 0 0 1 0 0 0. So this is the case of overlapping not allowed. So actually what happened is that first it detected this sequence, then it detected this sequence. So 2 times your output was 1. 2 times your output was 1. If overlapping was allowed, then what was the scene? Overlapping allowed, the same sequence I need to detect. So what do you think what will happen? So first it will detect this sequence 11011. Then again you can see 11011. Then again you can see 11011. Then again here you can see 11011. So 4 times your output will be high. Let's check. First what will happen? 1 will come, 0. Then 1 1 will come, 0. Then 1 1 0 will come, 0. Then 1 1 0 1 1 will come, 0. Till then everything is same. Till this cycle everything is same. Now 1 1 will come, 1. Till this also everything is same. Now just as this cycle comes, just as this is being detected, when it was overlapping not allowed, it was getting cleared, but here it will not get cleared. What will happen is that in the next cycle 1 1 0 1 1 and next 0 will come, but it cannot have 6 bits because in the register you can only have 5 bits, so it cannot have 6 bits. So this one it will clear. So now you are having 1 0 1 1 0 1 0 1 1 0, output will be still 0. In the next state, this one will be cleared. So 0, 1, 1, 0 and 1 will come. So again output is 0. Then in the next state, this 0 will be cleared. So 1, 1, 0, 1, 1 will come. Yes, it is being detected. So if it is detected, your output is 1. Now in the next cycle, this one will be gone. So 1, 0, 1, 1, 0. Output is 0. Then in the next cycle, this one will be gone. So 0, 1, 1, 0, 1. Okay, output will be 0. Then in the next cycle, this 0 will be gone. So 1, 1, 0, 1, 1. Yes, output is 1. So this is also detected. Okay, I should have written it more small. Let's do anything. Can we do anything? Yeah, it works. Okay, I hope you will be able to understand it. So 1, 1, 0, 1, 1 is coming. Till this point we have reached. Okay, till what point we have reached? Till this point we have reached. Okay, 1, 1, 0, 1, 1. Now in the next cycle, this will be cleared. So 1, 0, 1, 1 and then 0 will come. So again 0. Then in the next cycle, this will be cleared. So 0, 1, 1, 0, 1 will come. So again 0. In the next cycle, 1, 1, 0, this 0 will be cleared and 1, 1 will come. So this is again detected. So this is also 1. So what is your output? 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1. So 4 times you will be getting 1. So if in the question this is asked that how many times your output will be 1. So better you will see, okay, overlapping allowed 1, 2, 3, 4 in that manner. Here we saw now 1, 2, 3 and 4. 4 times your output will be 1. And here overlapping is not allowed. So once, then all clear. Then start looking from here, not giving, this is giving. And again 1, all clear. Then start looking from here, not giving, okay, only 2 times. So these kind of questions are asked usually in your GATE examination. But we will study about the designing as well. That is a very important part and very, very intuitive. And usually people find it very, very difficult and usually it is ignored as well. But we will see the in-depth analysis, we will see whatever that can be covered. So in the next video that we will see, but we will see the designing part as well. How to design overlapping and non-overlapping sequence detector using Mealy machine, using Moore machine. Okay, so that we will see in the next particular video, but let's solve a GATE problem. So a sequence detector is designed to detect precisely 3 inputs with overlapping sequence detectable. For the sequence detectable, overlapping is allowed. You need to detect the sequence 101 and input data is 1101. So input data is, okay, I need to add a page. So input data is 110, 110, 100, 110, 100, 110, 101, 10, 101, 101, 10, 10. Okay, so I will see again 100, sorry, 110, 100, 110, 110, 100, 110, 101, 10, 101, 10. Okay. Okay, then, and you need to detect the sequence 101, 101. So first 1 will come, output will be 0. Then 1, 1 will come, output will be 0. Then 1, 1, 0 will come. What I need to detect? 101 I need to detect. 101 I need to detect. Again output will be 0. In the next cycle what will happen? 101 will come. This one will also come, right? 110 and then another one. But this will be cleared. Why this will be cleared? Because only 3 bits can be there in the register. So yes, output will be 1. Okay. After that, this one will be gone, 010, output will be 0. Then this will be gone, 100, output will be 0. Then this will be gone, 001, output will be 0. Then this will be gone, 011, output will be 0. Then this will be gone, 110, output will be 0. Then this one will be gone, 101, yes, output will be 1. After that, where we have reached 101, so this will be gone now. So 0, 1, 0. Output will be 0. This 0 will be gone. I hope you are able to catch up. Okay, 1 0 1 we have reached, 0 1 0. Now 0 1 0. Now this is gone. 1 0 1. This will be again 1. Then this one will be gone. 0 1 1. So this will be 0. After that 0 will be gone. 1 1 0. This will be 0 only. And after that you will be left with 2 bits, certainly it is 0, then 1 bit, certainly it is 0. So what is the output sequence you are having? 0 0 0 1 0 0 0 0 0 1 0 1 0 and then 3 times 0, right? But in the option what do you see? In the end you see only 2 0 and in the beginning you only see 1 0. Why is that so? Because usually in the options what they can do is that they will check the output only when there are 3 bits in the register. So only these outputs they are checking. Okay. So usually this is what they can do. Only these outputs there. They are not considering these 2 0. They are not considering these 2 0. So this 0 and this 0 they are not considering, and this 0 and this 0 they are not considering. So 0 1 then 5 times 0, 0 1 then 5 times 0, then 1 0 1 and then 2 times 0. So that's the output you are getting. So this is the option A. So this is how the options can be framed, where they will not consider the states where you are having less than 3 bits. Here you are having 3 bits, so they will consider it. But if you are having less than 3 bits, they will not consider the states. So here you are having 1 1 1 1, but they are not considering these 2 states, okay, and these 2 states as well. So this may happen in the options. So for this particular example, what could be the option given? They will not consider this state, they will not consider this state, they will not consider this state, they will not consider this state. They will consider the state where you are having 5 bits input. Okay, 5 bits should be there. So 5 bit is there, 5 bit is there, 5. So they can give the output as 1 0 0 1 0 0 1 0 0 1. There you go. Okay, so this is how they can frame their output. So they can consider 5 bits. So these kind of questions can be framed in your gate examination. Even in the interview as well, they can ask these kind of questions, and even in what we say, even in your written examination of placement also these kind of questions can come. So I hope you must have understood this particular concept, that is the how do we detect a particular sequence, overlapping allowed, overlapping not allowed. And the important thing is you need to see that only 5 bits will be there in the register if we are detecting the 5 bits, and if we are detecting the 3 bits, there should be 3 bits in the register. Okay, and in case of overlapping allowed, the register doesn't get cleared. It will keep on going 5 5 5 5 5. But in case of overlapping not allowed, once you detect the sequence, all gets cleared. Once I have detected the sequence, everything is getting cleared. I am again starting from 0, again starting from the next bit. Okay, so I will start right from the beginning. Once I detect a particular sequence, I will start right from the beginning. So that's a very important point. It will be highly used in our next video. So what I am saying? I am saying that in case of overlapping not allowed, once you detect the sequence, your register gets cleared. You start again from the beginning, that is 0. So here I am starting from here. Okay, so in case of overlapping allowed, your register doesn't get cleared, only one of the bits is removed. You again see there are 5 bits altogether. Okay, then in the next video we are going to study about designing a particular sequence detector. How do we design a particular sequence detector? So very important point, very important topic, and you need to give me full concentration, then only you will be able to understand it. Okay, then so let's meet you in the next video. Next video will be very interesting. Thank you very much. Hi everyone, we have been studying about sequence generation and detection. So in the last video we saw everything about sequence generation. So we saw the circuit as well, and we saw the meaning of sequence generation as well. Then we were studying about sequence detector. So there we saw that there will be 2 kind of outputs, overlapping allowed, overlapping not allowed. So there will be a sequence detector circuit. You will apply a input bit stream. If overlapping is not allowed, it will detect the sequence once and twice. So twice it will detect the sequence, and if overlapping is allowed, then first it is detecting, then again detecting, then again detecting, and then again detecting. So 4 times it is detecting. Okay, so there were 2 cases, overlapping allowed and overlapping not allowed. So basically there will be a state machine, or you can say there will be a circuit to which you will apply some input. just as you have applied the input, it will start giving you the output, right? If the sequence is detected, in this case it is detecting 11011, just as it is detected, it will give output 1. In case of overlapping not allowed, just as it is detected, very important line, just as the sequence is detected, the whole register gets empty and you start right from 1 bit. Just as the sequence is detected, it will completely get empty and you will start right from the beginning again. In case of overlapping allowed, just as it is detected, it is not getting empty, it is carrying the previous bits. Just as it is detected, doesn't carry the previous bits, doesn't carry previous bits in next cycle. Very important point, the whole lecture will be based on this only. Okay, carries previous bits in next cycle. Very important point. Okay, and oftenly it is ignored by the aspirant. If they are asking good question from you, then this concept will be used. So let's start designing our sequence detector. Now what is our task? Our task is to design this particular machine. Here we saw how it will give the output, but how we will design this? This also we will design. We know how output comes. This is the input stream that user will apply, but how to design this, that we are going to see now. So now we are going to design sequence detector. So for a particular sequence, let's just say I need to detect 11011. So for this particular sequence, detection, there can be 4 type of machines. 4 type of machines are possible. Overlapping allowed, overlapping not allowed. And in case of overlapping allowed, Mealy machine. Overlapping not allowed, Mealy machine. Overlapping allowed, Murray. Non-overlapping, Murray. Right? To detect a particular sequence, there could be 4 type of machine. Overlapping allowed, Mealy. Non-overlapping, Mealy. Overlapping allowed, Murray. Non-overlapping, Murray. Okay. Now this statement you will not understand as of now, that the number of bits in the sequence, let's just say if number of bits, this is the sequence that I want to detect, 11011. So how many bits are there in the sequence? 5. So in case of Mealy type, you would require 5 states only. There are 5 bits, right? There are 5 bits. So in case of Mealy type, you would require 5 states. And in case of Murray type, you would require 6 states. One more state. When we see the example, it will be more clear to you. Just I wanted to write down this point because this is also very important point. Okay. So in case of Mealy, equal to the number of bits, and in case of Murray, one more than that. So let's start with our first example now. So which sequence you need to detect? You need to detect the sequence 11011. Okay. So number of bits are 5. So let's just say I am in any state. I am in state A. This state could be anything, 000, this 00101, it could be any state. But currently I am in state A. I am starting from state A. This is my starting point. This is my starting point. Now, if my applied input is 1, what I am doing, this is my FSM. This is the state that I am designing, and from here I am applying the input. If my applied input is 1, then I will be happy, because if applied input is 1, then I can go to the next state now. Because if applied input is 1, then I am on right path. So if applied input is 1, then I can go to the state B. Next state I can go, which is my state B. What will be the output I will be giving? 0 output only, no? I will not be giving but 1 output until I detect the complete sequence. Until I detect the complete sequence, I will not give 1 output, right? You see here, overlapping not allowed case we are doing. Overlapping not allowed case. Until you detect the complete sequence, you are not going to give output 1. Okay? So this is the overlapping not allowed case we are seeing now. Okay? Overlapping not allowed. Then again, if I get 1, if my applied input is 1, then I can go to the next state C. If my applied input is 0, then I can go to the next state D. And if my applied input is 1, then I can go to the next state E. So basically the scene is, if I am at B, that means sequence 1 has been detected. Okay. If I am at state C, that means certainly sequence 1 1 has been detected. If I am at state D, that means certainly 1 1 0 has been detected. If I am at state E, that means certainly 1 1 0 1 has been detected. Say yes or no. If I am at state B, 1 has been detected, then only you are coming to B. If you are at state C, then 1 1 has been detected. If you are at state D, then 1 1 0 has been detected. If you are at state E, then 1 1 0 1 has been detected. Now, if I apply input 1 again, I am at state E. If I get 1 again, then my job is done, right? My output will be 1 now. My job is done. If at state E I apply input 1, then job is done, output will be 1. So if the job is done, in case of overlapping not allowed, in case of overlapping not allowed, if the job is done, we start our work right from the beginning again. Just as the job is done, we will start the work right from the beginning again. So just as the job is done here, just as the job is done, it will start the work again. So if 1 is applied, it will give output 1 and will start the job again. So 1 1 0 1 1. So this sequence has been detected. 1 1 0 1 and 1. And just as you get this sequence, your output is 1 now. Okay, but we need to take other cases as well. What if the first input was 0 only? If applied input was 0 only, you will come back to the same state. You will start from A only, because if applied input is 0, you cannot proceed. Now if you are at state B, that means 1 has been already applied. If you are at state B, that means input has been 1 already, that's for sure. In the next state, if I get 1, then I know I need to go ahead, because that is the sequence that we want. But what if I get 0? If I get 0, then what I will do? If I get 0, then I know that I have to go back to again A only. If I get 0, I will have to go back to again A only, because I will have to start right from the beginning again. If I get 0, then I will have to start right from the beginning, because what I am gonna do is that I will drop 1 bit, I will look for this bit, which is 0. Do I see 0 anywhere? Do I see 0 here? No. Do I see 0 here? No. Do I see 0 here? No. The complete bit has to be 0. That I do not see anywhere. Here I get 0, but there are 3 bits, no. So there is no state which is already giving me 0. No, nothing like that. So I will come back to state A only. What about C? In case of C, if I get 0, then I will go to the next state. If I get 0, then I will go to the next state, that is D. That I know. But if I get 1, then where will I go? What do you think? Will I go to A, or will I go to B, or will I come back to C only? What do you think? If I get 1, if I get 0, I am proceeding. If I get 1, then where will I go? What do you think? Look, here you can see, if you drop 1 bit, here you can see double 1. And where you are getting double 1? You are getting double 1 at C only. Basically, if you are at C, that means certainly you have already got double 1. Now you are waiting for the next input. If next input applied is 0, then you are going to the next state. If next input applied is 1, then what you will think? That these two bits are still useful. Why these 2 bits are useful? Because let's just say I get this sequence. My first applied input was 1, then again it was 1, then again it was 1, then it was 0, then again 1, then again 1. So here it will say that the sequence has been detected. So these 2 bits have been used, and it will start from C only. After C, it will see that 0 is applied, I will go to D. After that, it will see that 1 is applied, I will go to E. After that, it will see that 1 is again is applied, I will go back to A. So what you need to do, basically, how we see it, how you can do it quickly, that is, now I am at state C, that means 1 1 has been applied. If 0 is applied, I know I need to go ahead. If 1 is applied, then I will drop 1 bit, I will look for these 2 bits. Do I get 1 1 anywhere? Yes, I get 1 1 in C only. So if I apply 1, my output will still be 0, sequence is not detected, but I will come back to C only. What about D? 1 1 0. If 1 is applied, I am going to the next state. But if 0 is applied, I will drop 1 bit, I will look for 1 0 0. Do I see 1 bit 0 0 here? No. Then I will look for 0 0 only. Do I see 0 0 here? No. Then I will look for single 0. Do I see single 0 here? No. That means I will have to go back to state A only. So I will have to go back to state A again. Okay. So if 0 is applied, output will be 0 and have to go back to state A. What about E? 1 1 0 1. If 1 is applied, I will have to go back to state A, because my sequence will be completed, my output will be 1. But if 0 is applied, what I will see? I will drop one bit, I will see, do I see 1 0 1 0 anywhere? 1 0 1 0, no. Do I see 0 1 0 anywhere? 0 1 0 here? No. Then I will look for last 2 bit. Do I see 1 0 anywhere? 1 0 here? No. Do I see single 0 here? No. That means certainly I will have to start right from the beginning again. So better making another line, it is written in this manner only, that just a second, I will keep this a bit here, and it is written in this manner only, that if 0 is applied, you will go to state A giving the output 0 only. Then again full cycle you have to start. So this is the state diagram. I know it is not very easy, like people will make it very complex. Okay, this is very tough to understand as well, that also I know, but we have understood the concept behind it, and now we have made a way to make this table. What is that way? That first you write down the condition, that how you are going to proceed when you are getting the one output, then you see which all bits have been remaining. Okay, and based on that you see in which state you are going. Okay, let's take another example. Overlapping not allowed only in case of melee. Overlapping not allowed, you need to detect 1 0 1 0. Overlapping not allowed in case of melee, you need to detect 1 0 1 0. So this is my starting point. I am starting from state A. If 1 is applied, yes, I am happy, because 1 0 1 0 I need to detect. So if 1 is applied, I will go to the next state. Then if 0 is applied, then I am happy, I will go to the next state. Then if again 1 is applied, I am happy, I will go to the next state. Then again if I am at A, that means this is my starting. If I am at B, then certainly 1 has been detected. If I am at C, then 1 0 has been detected. If I am at D, then 1 0 1 has been detected. If applied input is 0, then my job will be done and I will be coming back to A only. If applied input is 0, job is done, I am coming back to A only, right? Now in the initial only, if I am getting 0, so this is not I want, I will start again here at B. If I get 0, I know I need to go ahead, right? But if I get 1, what I will do? I will drop one bit, I will see, do I get 1 anywhere? Yes, I get 1 in the state B only. So if applied input is 1, I will get output 0, but I will come back to state B only. Why I am not going to A? Why should I start from the beginning? Because this 1 can be used in the next analysis, in the next stage. To go for the next state, this 1 can be used. That's why I am not going to state A again. I am staying at state B only. Because what if the sequence is 1 1 0 1 0? So this 1 can be used. So that's why I got to know that B, if I am at state B, that means 1 has already been applied. So why should I start from A? I will start from B only, no? Right? Now let's come to C. If I come to C, what do I know? That if 1 is applied, I need to go to the next state. But if 0 is applied, then I will have to think. So what do I see? That do I get double 0 anywhere? No. Do I get single 0 anywhere? No. Then certainly I will have to start from A only. Because this sequence can never be used. Anyhow, this sequence can never be used. Let's just say next bits are 1 0 1 0. So this 1 0 1 0 will be detected. There is no use of that. So certainly you will have to start from A only. Are you getting this point? Slowly you are understanding, right? Now I am at state D. So if 0 is applied, I know I need to go here. But if 1 is applied, now I will look for the best case. Which is the best case? Let's see. 0 1 1. 0 1 1. Do I get 0 1 1? No. Do I get 1 1? No. Do I get a single 1? Yes. So this 1 is of some use. This 1 can be useful for me. So where I am getting? At state B. So from here to, I will go here. Are you getting this point? In the last state 1 0 1. If 0 is applied, I will have to start right. If 0 is applied, my job is done. Now I will start from the beginning. But if 1 is applied, then I will look for the best case. 0 1 1. 0 1 1. 0 1 1 not getting. 1 1 again not getting. Single 1, yes I am getting. So this 1 can be of use. Single 1 I am getting here. So I will go to this state. So if applied input is 1, then output will still be 0 and I will go to this state. Now let's just say if this diagram is given in front of you and they ask you which sequence it will detect. Can you tell that? which sequence this state diagram will detect. Yes, we will start from A. You will see when do I go to the next state? When applied input is 1. When do I go to the next state? When applied input is 0. When do I go to the next state? When applied input is 1. And when do I get the final output? When applied input is 0. There you go. This is the sequence that is detected. So this is how you can do. Okay. These kind of questions are easy, but if they are asking to design, that becomes a bit typical. But designing part is also important. Okay, because that can be used. Now what else can be asked? So here there were 4 bits, right? 4 bits. 4 bits means you require 4 states. And 4 states means how many flip-flop you require? 2 flip-flop, right? Basically your A can be 0 0, B can be 0 1, C can be 1 0, and D can be 1 1. So how many flip-flop you require? 2 flip-flop you require. In this case, number of bits were 5, that means 5 states were there. 5 state means how many flip-flop? 3 flip-flop you require. Okay, so they can ask you to detect this particular sequence, how many flip-flops you will require. So what you will do? 5 bits are there, that means there will be 5 states. If 5 states are there, then certainly 3 flip-flops will be required. In case of melee, whether it is overlapping allowed or not allowed. In case of melee, this will be the answer. Now let's see the case of overlapping allowed. Now overlapping is allowed. In case of overlapping allowed and overlapping not allowed, what was the difference? Till this point everything was same. But when the sequence was detected, at that time there was difference, right? When sequence was not detected, there was no difference. But when the sequence was detected, after that the difference came. What was the difference? This guy was starting right from the beginning again. Right from the beginning again. But this guy is not starting right from the beginning. It will carry the previous bits. It will carry the previous bits. And in the next cycle, what do we go to know that? This double one has been used. You can see that this double one has been used. This double one has been used. This double one has been used. So that has been used. So previous bits can also be used. Even after detecting the sequence, previous bits can also be used in case of overlapping allowed. Okay, so now we are going to make the cycle for, or we should say state diagram for the case of overlapping allowed. So now your overlapping is allowed. So what I am going to do, what I need to detect? 1 1 0 1 1. I will start from A only. If applied input is 1, I am happy, I can move to the next state. If applied input is 1, again I am happy, I can move to the next state. If applied input is 0, I am again happy. I am again happy and I can move to the next state. Did I write 1 here? No. ये सब blunder तो नहीं किया ना मैंने. Yeah. Now if I applied input is 1, then I can move to the next state. And now if my applied input is 1 again, so here I will pause. Okay, so we will analyze this. So if I'm at B, then that means 1 has been detected. If I'm at B, then 1 has been detected. If I'm at C, then certainly 1 1 has been detected. If I'm at D, then 1 1 0 has been detected. If I'm at E, that means 1 1 0 1 has been detected. Right? Now if applied input is 0, at E I am talking about, at E, if my applied input is 0, sequence is not detected now, right? Sequence is not detected. 1 1 0 1 0, this is not you wanted 1 1 0 1 1. So if applied input is 0, sequence is not detected, then it will look for best possible case. What is that? 1 0 1 0, getting anywhere? No. 0 1 0, getting anywhere? Wait a second. So at state A I am at 1 1 0 1. So if 0 is detected, if applied input is 0, so it will look for the best case. 1 0 1 0, are you getting anywhere? No. 0 1 0, are you getting anywhere? No. 1 0, are you getting anywhere? No. 0, are you getting anywhere? No. So it will start right from the beginning only. This is the case for if applied input is 0, then sequence is also not detected, also you have to start right from the beginning. Now if my applied input was 1, now it will again start looking for the best case. Why it is starting? It will start looking for the best case. If your applied input is 1, you know one thing, that is my output is going to be 1 now. If my applied input is 1, if my applied input is 1, my output is going to be 1. But where it will go? It will go to the initial state. No, this is the case of overlapping allowed. If overlapping is allowed, then if overlapping is allowed, you see here the overlapping was allowed. So it was not starting from the beginning. It looked for the best case that these two 1 1 can also be useful for me. these two 1 1 which I am getting in this state, these can also be useful for me, because what if in the next states I get 0 1 1? So now it will look for the best case. So 1 1, sorry, here. So if I am at state E, that means 1 1 0 1 has been already detected. Now if 1 is applied, it will start looking for the best case, which is, do you see 1 0 1 0 anywhere? No. Do you see 0 1 1 anywhere? No. Do you see double 1 anywhere? Yes, I see double 1 at state C. So it will go to the state C. Are you getting this point? Because double 1 can be useful, because what if in the next cycle this comes? So sequence will be again detected. Sequence will be, first this was detected and then again detected. So in next 3 cycles only sequence can be detected, from C to D, D to E, and then E to again C. I can go in this manner, because these two ones can be of use. So again it will look for the best case. So that's the difference only. Here the major difference comes. Then when the sequence is detected, in the previous case I was starting right from the beginning when sequence was detected. But here, if sequence is detected, it will again look for the best case, which is this. So that's why it is going in this manner. Right? Understood? Now what about other cases? These cases will be same. Because if 0 is applied, it will have to start from the beginning. If you are at B, 0 is applied, then 0 it cannot see anywhere. So it will start from the beginning again. What about C? If 0 is applied, it need to go ahead. If 1 is applied, it will look for the best case. What is the best case? 1 1. C itself. So if 1 is applied, it will come back to C only. What about D? If 1 is applied, it will go to the next state. But if 0 is applied, it will look for the best case. That is 1 0 0, not anywhere. Double 0, not anywhere. Single 0, not anywhere. So it will have to go back to state A. So if 0 is applied, output will still be 0. And for E also we have analyzed. So I hope you are understanding the point, right? Let's do it again for this sequence, which is 1 0 1 0. We are going to do it for 1 0 1 0. Okay. So I am currently at state A. If applied input is 1, if applied input is 1, then I am happy. I can go to the state B. This is the case when overlapping is allowed. If applied input is 0, then I am happy. I can go to the next state. If applied input is 1, then I am happy. I can go to the next state. If applied input is, now I will check. So if I am at B, that means 1 has been detected. If I am at C, then 1 0 has been detected. If I am at D, that means 1 0 1 has been detected. Now at D, if 1 0 1 0 has been detected, next input bit is 0. If next input bit is 0, then what it will say? That my output will be 1 now. Output will be 1. There is no doubt about that. But it will look for the best case now. And what is the best case? Do you see 0 1 0 anywhere? No. Do you see 1 0 anywhere? Yes. I see 1 0 to the state C. So it will go to the state C. So if applied input is 0, then sequence is detected, it will give output 1, but it will go to the best case, which is 1 0. So it will come back here, right? And if the applied input was 1, if the applied input was 1, so eventually it have to look for the best case only. Output will be 0. If applied input is 1, output will be 0. But again it will look for the best case. Which is the best case? 0 1 1. Do you see? No. 1 1 do you see? No. Single 1 do you see? Yes. Single 1 I see. That means I will go here. So if applied input is 1, my output is 0 only, but I can go to the state B. Say yes or no. Right? Let's analyze the same for the rest of the states, which is this. If applied input is 0 initially, I will come back to A only. After 1, if applied input is 0, I am going ahead. If applied input is 1, so I will look for the best case. Which is the best case? Drop 1 bit. Do you see 1 anywhere? Yes, I see 1 at B only. So if applied input is 1, I will come back to B only. Do you got this point? 1 1, drop 1 bit. You see, if 0 is after 1, if 0 was applied, I need to go to the next state only. But if 1 is applied, I will see for the best case. Drop 1 bit. Where is 1? Where is 1? In the state B itself. So if applied input is 1, give output of 0 and come back to state B only. This we have already analyzed. Now in the state C, if applied input is 1, I will go to the next state. But if applied input is 0, I will look for the best case. Which is the best case? Do I see double 0 anywhere? No. Do I see a single 0 anywhere? No. So I will have to go to the state A only. There is no other chance I am having. So if applied input is 0, then I will give my output equals to 0 and will go back to state C. And for D only we have analyzed, right? For D we have already analyzed, right? Did we see another example? So this you will do on your own, but later on you will do. So yeah, that was the scene for Millie machine. So this we have done for Millie machine. Overlapping allowed and overlapping not allowed. Murray will be exactly the same, but what is the case in Murray? In case Murray, the output is already written. So I will be starting what I need to detect. The example is 11011 11011. This I need to detect, right? Now I will start from state A, considering my output is 0. Why I already consider my output to be 0? Because if I am starting, then certainly I am not getting output 1, because I need to detect 5 bits. I need to detect 5 bits, and if I am starting at the first, I will get only 1 bit. So no matter whatever the bit I get, whether I get 1 or 0, certainly my output is going to be 0 only, no? Because I need to detect 5 bits. So for that, if my applied input is 1, then I can go to the next state. Again my output will be 0 only, right? If my applied input is 1, I can go to the next state, but again output will be 0 only. 1, 1. If my applied input is 0 now, then I can go to the next state. I can go to the next state, but again output will be 0. If my applied input is 1, then I can go to the next state, but again my output will be 0. Okay, I should have made it a bit more small. Yeah, so what I have applied 1101. Again, if I apply 1, I can go to the next state. A, B, C, D. 1 is applied, 1 is applied, 0, 1 is applied, and again 1 is applied. So I can go to the next state F. Now my output will be 1. Say yes or no. 1, 1, 0, 1. Till this point your output was 0. If again 1 is applied, you will go to the next state, but now your output is 1. So that's why I said you require one more stage. Okay, so better here only I can make no issue about that. You will get output 1. So you need one more stage here. You can see here you required A, B, C, D, E, but here you require one more stage, that is showing that your output is 1 now. So you started with A, output was 0 only. Why output is 0? Because you know that in one state only you are not going to get output 1. Then if bit 1 is applied, then you are happy, you can go to the next state. Then again 1 is applied, you are happy, you can go to the next state. Again 0 is applied, you are happy, you can go to the next state. Again 1 is applied, you are happy, you can go to the next state. But here what do you see? That now my output will become 1, because the sequence has been detected. Okay, right? Now let's see, if I am at state B, that means certainly 1 has been detected. If I am at state C, that means 1 1 has been detected. If I am at state D, that means 1 1 0 has been detected. If I am at state E, that means 1 1 0 1 has been detected. And if I am at state F, that means 1 1 0 1 1 has been detected, right? Now let's start with A again. If 0 is applied, I will come back to A only. In front of B, if I am at B, then certainly 1 has been already there. If 0 is applied, I will look for the best case. No best case is there, I will have to go to A only. What about C? If I am at C, that means 1 1 has already been applied. If 0 is applied, I am going to the next state. If 1 is applied, I will look for the best case. What is that? C itself. So I will come back to C only. Now if I am at D, if I am at D, that means 1 1 0 has been applied. 1 1 0 has been applied. If I am at D, that means 1 1 0 has been applied. If 1 is applied, I am going to the next state. But if 0 is applied, I will look for the best case. 1 0 0, can't see anywhere. 0 0, can't see anywhere. Single 0, can't see anywhere. Again I will have to start from A only. For the applied input 0, right? What about this one? 1 1 0 1. So if applied input is 1, I am going to the next state. But if applied input is 0, I will look for the best case. What is that? 1 0 1 0, see anywhere? No. 0 1 0, see anywhere? No. 1 0, see anywhere? No. Single 0, see anywhere? No. So if applied input is 0, you will have to again start from A only. Now in this case, 1 1 0 1 1. The case is overlapping not allowed. Overlapping not allowed. So you are supposed to start right from the beginning. Will you start from A only? No, you need to check. No. If you are at F, then 1 1 0 1 1 has already been detected. If 0 is applied, if 0 is applied, if 0 is applied, then certainly you have to start right from the beginning. I am not looking for the best case here. I am not looking for the best case. If 0 is applied, this, if this has been detected, this is gone now, right? Now my new journey will start. My new journey is starting from 0. So my new journey is not matching from anyone here. I will repeat this point. Listen to me very carefully. If 1 1 0 1 1 has been detected, that means this loop is gone now, right? There is no use of this loop, because this is the case of overlapping not allowed. In case of overlapping not allowed, if 1 is detected, then it is gone. We'll start our new journey. We are starting our new journey. If I am starting my new journey and I get 0 there, so I will match. If in any of the previous state am I getting 0? No. Then I will have to start again from A only. But if I get 1 in the next state, if I get 1, my applied input is 1. So will I start from A again? No, I will start from B. Mark my point, I am not overlapping here. This is not overlapping. These bits are gone. But my next applied input is 1. My next applied input is 1. If my next applied input is 1, what will I think? Why should I start from A? Because directly I can start from B only. No, because B is saying that I am already at state B. That means already 1 has been applied. So if 1 has been already applied, then I should start from B only. No, say yes or no. This is not overlapping. If I was overlapping, then I would look for 1 1, and 1 1 is here. I would go to C, not to B. But I am going to B because these bits are gone now. What is left? This 1 is left. Now this 1 is left. Now you will see what is the best case for this 1. The best case for this 1 is B. So that's why you are going to B. If my applied input is 1, what I will think? Yeah, this is my new journey. Journey is new now. But if I applied input is 1, then I will go to that shop which is already having 1. Why should I go to the shop where I started? No, I will go to the shop where it is already having 1. So I am going there. This is not overlapping. We will see the case of overlapping. That will be different. So this was not the case of overlapping. Okay. So I hope you must have understood. Now in this example only we will see the case of overlapping, because guys get confused in this particular example. Okay. So let's see the case of overlapping. So A0 will be there. So what I need to detect? 1 1 0 1 1. So if applied input is 1, I will go to the state B. If applied input is 1, I will go to the state C. If applied input is 0, I will go to the state D. If applied input is 1, I will go to the state E. And if applied input is 1 again, I will go to the state F, giving the output equals to 1. So 1 1 1 1 1 0 1 1 0 1 1 1 0 1 1. There you go. Okay. Now in case of BCD, everything will be same. Until the sequence is detected, everything will be same only. So no need to worry about these cases. But let's analyze it. If applied input is 0 itself, I will come back here only. Right? If applied input is 1, in case of B, if applied input is 1, then I am going ahead. But if applied input is 0, if I am at B, that means 1 has been already detected. If 1 is applied, I am going ahead. If 0 is applied, I will look for the best case. I am not getting anywhere. So I will come back here only. In case of C, if I am at C, that means 1 1 has already been applied. If I get 0, then I am going to the next state. If I get 1, that means I will look for the best case. That is 1 1 only. So I will come back to C only. Applied input is 1, I am coming back to C only. What about this? 1 1 0. If applied input is 1, I am going to the next state. If applied input is 0, I will look for the best case. 1 0 0, not getting anywhere. 0 0, not getting anywhere. Single 0, not getting anywhere. I will have to go to state A only. What about this? 1 1 0 1. If I am at state C, that means this has been detected. If I apply 1, I will go to the next state. If I apply 0, If I apply 0, I will look for the best case. 1 0 1 0, not getting anywhere. 0 1 0, not getting anywhere. 1 0, not getting anywhere. Single 0, not getting anywhere. That means I will have to start from the beginning only. Now the interesting thing will come. So this is the most important part which is required. So now let's see for this part. So sequence has already been detected, that you know, 1 1 0 1 1. But if the applied input is 0, if the applied input is 0, it will look for the best case only. It will look for the best case only, no? If applied input is 0, it will again look for the best case. That my sequence is not detected. If applied input is 0, my output will be 0 only. But what if I get the best case? That what if I get 1 1 0 1? If I get 1 1 0 1, I can come back here. But am I getting that? What I am getting? 1 0 1 1 0, not getting anywhere. 0 1 1 0, not getting anywhere. 1 1 0, yes, I am getting here. So I will go to the state D. If my applied input is 0. If my applied input is 0, then this is the scene, that this is the scene. So 1 1 0 is already there. 1 1 0 is already there. What if in the next cycle 1 1 comes? So this was already detected, 1 1 0 1 1 0. This will also be detected. So this 1 1 0 has been used. Are you getting this point? This 1 1 0 has been used. So that's why I went to the state D. Now, if applied input was 1, then again I know my output is not going to be 1. My output is not going to be 1, but again I will have to look for the best case, because in case of overlapping allowed, my final state will always look for the best case. In case of overlapping allowed, my final state will always look for the best case. But in case of overlapping not allowed, it will have to think. But in case of overlapping allowed, my final state will always look for the best case. If you are not understanding these points, I highly recommend you to watch the video again. You will understand. But this is the best way it can be taught. Okay, you can watch n number of videos on this particular topic, but I guess this is the only explanation where I have put like all the possible chances the way I can explain. So I hope you are understanding. So now again it will look for the best case, which is 1 0 1 1. It is getting anywhere. 1 0 1 1, no. 0 1 1, no. Triple 1, no. Double 1, yes. Double 1 it is getting. So double 1 it is getting at C. So it will go to C. Okay, and this I can make better. From here I can make it. It would have gone to D for applied input 0. If applied input is 1, it will go to C. Because these two 1 1 can be used in the next cycle. 1 1 0 1 1. So these two 1 1 can be used. What if 0 1 1 is applied? So these two 1 1 can be used. So that's why it is going here. So this is the overlapping allowed Moore. So this is how we make it. Are you comfortable with this analysis? No, you are not comfortable, I know. But I highly recommend you to watch it again. Once you feel like that you are comfortable, then try this. Overlapping not allowed Moore. Overlapping not allowed Moore. What you need to detect? 1 0 1 0. Look, if they are going to ask you to design, then mostly they will ask for 3 bits only. For 5 bits, that's the maximum. Okay, that's the maximum limit. If they are asking to design, to detect, they can ask anything, because detecting is very easy. If I am asking you to detect the sequence here, can you detect it? Yes, you just need to see when I am going to the next state. If 1 is applied, I am happy going next state. 1 is applied, again 0 is applied, 1 is applied. Just as 1 is applied, my output is becoming 1. So that's it. This is detected. It is very easy. Right? Whenever it is detected, output is 1. So detecting is very easy. But to design, you need to think. So here we are designing. Right? So now we are designing for overlapping not allowed Moore. So initial state, if 1 is applied, I am happy. I will go to the next one. If 0 is applied, I am happy. I will go to the next one. If 1 is applied, I am happy. I will go to the next one. And if again 0 is applied, then I am super happy and I will give my output equals to 1. So if I am at B, that means 1 has been detected. If I am at C, that means 1 0 has been detected. If I am at D, this has been detected. If I am at E, this has been detected. Let's talk about this point at B. If applied input is 0, I am going ahead. If applied input is 1, I will look for the best case, which is 1 itself. So I will come back here. And what about this A? If 0 is applied, I will come here only. But we cannot write output here. If 1 is applied, then I will come back to state B only. 1 is applied, I will come back to state B only, right? What about this case? About C. If 1 is applied, I am going ahead. If 0 is applied, I will look for the best case. Double 0, do you get anywhere? No. Single 0, do you get anywhere? No. Then I will have to go back to A only. For which input? For applied input 0. What about D? 1, 0, 1. If 0 is applied, I am going to the next state. If 1 is applied, I will look for the best case. 0, double 1, no. Double 1, no. Single 1, yes. I am getting single 1 at B. So from D to B, I will be going. Single 1. I get single 1 at B. So from D to B, I will be going for applied input 1. Now, last case. What is the scene here? Overlapping not allowed. That we need to remember, overlapping not allowed. 1, 0, 1, 0. Sequence has been detected, that's for sure. Sequence has been detected, that's for sure. Now, if 1 is applied, if sequence has been detected and overlapping not allowed, that means this is gone. There is no use of that. Sequence has been detected, overlapping not allowed, this is gone now. Because in case of overlapping not allowed, if sequence is detected, then whole register gets cleared. Whole register gets cleared. So it is clear now. So now only you have to look at 1. Overlapping not allowed, Moria. So now you only have to look at 1. This is gone, there is no use of that. What you will say? That why should I start from the beginning? Because 1 I am getting in state B only. So if applied input is 1, then I will go to state B. If applied input is 1, I will go to the state B only. And if applied input is 0, then I am not getting any good case here. So then I will go to state A again. Are you getting this point? This is the case of overlapping not allowed only. This is the case of overlapping not allowed. Are you getting this point or not? Are you understanding? Overlapping we are not allowing. If I was allowing overlapping, the case would have been different. Here I would look for double 0. I am not getting double 0. Then I will look for 1 triple 0. That also I am not getting. 0 1 1 0 also I am not getting. But in case of 1, if overlapping was allowed, then I would look for this case 1 0 1 that I am getting at D only. I would go to D if overlapping was allowed. But here overlapping is not allowed. That means this 1 0 1 0 is gone. I am only looking at 1. So where do I get 1? I get 1 at B. So I am going at B. If you are thinking with good amount of patience, if you are thinking with a cool brain, you will be able to understand it, right? And to be very honest, in GATE examination till now they did not ask any question on designing, but certainly they can ask. Okay, this question is certainly on cards. It can any day come. In GATE examination, what do they ask? Usually to detect the sequence, and you people directly detect the sequence. They don't even ask whether it is overlapping or non-overlapping. And 9 out of 10 students, or I would say 10 out of 10 students, don't even know that state diagram will be different for overlapping and non-overlapping. So that is something that is missing. Usually we don't see lectures on FSM much on depth, but this is the maximum depth they can go. Even in the interview, this is the thing they will ask, not more than that. Okay, so I hope you are getting comfortable. If you are not getting comfortable, I highly recommend to watch the video again. You will understand everything slowly. Now your task is to design the same, but for the case of overlapping allowed. Overlapping allowed, Mure, you need to detect 1 0 1 0. Pause the video, do it on your own. Okay, so let's start doing it. Should be very easy for you. If 1 is applied, go to state B, output still 0. If 0 is applied, then I am going to state C. And if again 1 is applied, I am going to state D. And again 0 is applied, I am going to state E. And then if again if again 1 is applied, 1 0 1 0. Okay, sorry. Here only I am getting output 1. So here I was detecting 1, here I was detecting 1, here I was detecting 1, here I was detecting 1 0, here I was detecting 1 0 1, and here I was detecting 1 0 1 0. Say yes or no, right? 1 0 1 0. Now let's start from A. If applied input is 0, I will come back here only. If applied input is 1, here. If applied input is 0, I am going to the state C. And if applied input is 1, I will come back to B only. This we have already seen. What about C? If applied input is 0, then I will look for 0 0 not getting. I look for single 0 not getting. Then I will have to go back to state A. And if applied input is 1, I am going ahead. Right? What about this? 1 0 1. If applied input is 0, if applied input is 0, then I am going ahead. And if applied input is 1, if applied input is 0, I am going ahead. If applied input is 1, I will look for the best case. 0 1 1 not getting, double 1 not getting, single 1 yes getting. So if I am getting single 1, so I will go to the single 1, that is B. So if applied input is 1, I am going here. Now E comes. So sequence has already been detected, but this is the case of overlapping allowed. So you will take this in action. 1 0 1 0. So if applied input is 0, you will look for the best case. 0 1 0 not getting, 1 0 0 not getting, double 0 not getting, single 0 not getting. So certainly I will again have to start from A only. In case of overlapping allowed, if input is 0, but if input is 1, then again I will look for the best case. So 0 1 0 not getting anywhere, 1 0 1 yes getting in the state D. So I will go to the state D if applied input is 1. So I hope you are able to do it on your own now, because now this 1 0 1, this combination is useful. What if the next bit is 0? Then again I am detecting my output, right? So I hope you are understanding. I hope you must have done it. So these examples we have seen. First we started with 1 0 1 0, overlapping not allowed mile, overlapping allowed mile, overlapping not allowed mure, overlapping allowed mure, overlapping not allowed mile, overlapping allowed mile, overlapping not allowed mure, and overlapping allowed mure. Okay. Do this example. Only design mile machine. You don't need to design mure. Mure you can design on your own. Do the example 1 1 0. These kind of examples can be asked in your interviews. In gate examination, anything can come. Mostly they will ask this example only. You need to design overlapping allowed mile machine to detect the sequence 1 1 0. Okay. So what I will start from? I will start from A. If 1 is detected, then I am happy and will go to the next state. If again 1 is detected, I am happy and I will go to the next state. And then here I will wait. So 1 1. Now if 0 was there, so I would start right from the beginning only, giving the output 0. If in this case 1 is already detected, if I get 0, I will look for the best case. I will look for the best case. Do I get 1 0 anywhere? Sorry, do I get 0 anywhere? No, I do not get any 0 anywhere. So I will go to the state A again. Because if 1 is applied, if 1 was applied here, after B, if 1 was applied, I am going to C only. Now in case of C, if 0 is applied, that means sequence has been detected and you will have to start your journey again. This is overlapping not allowed actually. This I am doing for overlapping not allowed. Overlapping not allowed. So here 1 was detected, here 1 was detected. So if you apply 0, then your output will be 1 and you will have to start your journey again. But if you apply 1, then you will look for the best case. What is the best case? Double 1, do you get anywhere? Yes, I get double 1 in C itself. Basically in C you are getting 1 1. If you are getting 0, that means your journey was done and you have to start again, because this is the overlapping not allowed case. Overlapping not allowed case. In case of overlapping not allowed, just as the sequence is detected, you start your journey again. And in this case, if I am at C, that means I am at 1 1. If my input is 1, then I will look for the best case. What is the best case? Double 1. So double 1 where I am getting? At C itself. So at C itself. So if my applied input is 1, output will still be 0, but I will come back to C only. Understood? Let's start this one now. So these will be same only. There is no doubt about that. The changes will be there in the final state when it is detected, right? This I am making same. There is no doubt about that. So if I am at B, then 1 has been detected. If I am at C, then 1 1 has been detected. If my applied input is 0, then I know that sequence has been detected. If my applied input is 0, that means I know that sequence has been detected. But I will look for the best possible case. What is the best possible case? 1 0, do you get anywhere? No. Single 0, do you get anywhere? No. So again you will have to start from the beginning only. Are you getting this point? Here, this was the case for overlapping allowed. Overlapping allowed. So I will look for the best case that my sequence is detected. If my applied input is 0, my sequence is detected. But I will look for the best case because this is the case of overlapping allowed. So even in the final state, I am looking for the best case. Even in the final state, I am looking for the best case. So my best case is 1 0. Do I get anywhere? No. Do I get a single 0? No. So I will have to start from A only. Right? And if 1 is applied, then again I will look for the best case only, because eventually my output is going to be 0. So again look for the best case. 1 I get anywhere? Yes, here I get 1. So if 1 is applied, my output will still be 0, but I will come back to C only. That's the way I will be going. Okay. What do you understand here? What do you understand here? That these both are equal. And think with intuition, no. 1 1 0 in any sequence, whether it is overlapping allowed or not allowed, the answer will be same, no. Let's just say I am taking this sequence 1 0 1 1 0 1 1 1 0 1 0 1 0 1 1 0. I am saying you need to detect 1 1 0 in case of overlapping not allowed. Overlapping not allowed, 1 1 0 1 1 0 1 1 0 and then 1 1 0 in case of overlapping not allowed. Now I am saying detect 1 1 0 in case of overlapping allowed. Still the answer will be same. Still the answer will be same only. Overlapping allowed. Even if overlapping is allowed or not allowed, the answer will be same. Why is that so? Why the answers are same? Why these answers are same? Because there is no symmetricity in the sequence. Previous examples we took 1 0 1 0. You can see there is symmetricity. That again 1 comes, then again 0 comes. So yeah, these two sequences could be there. But what about 1 1 0? Again you have to apply 1 1. So 1 1 0 one sequence is detected, 0 1 1 is not the sequence. Again you have to apply 0 again. So this is the sequence detected. So overlapping is there or overlapping is not there, both are same only. So just by looking at the examples, if you just write down 1 1 0, you will realize that to again detect it, I need 1 1 0 again. So there is no symmetricity. So for overlapping allowed and overlapping not allowed, both cases will be same. So these kind of questions can be asked in your exam, in your interview, that you have made for overlapping not allowed. Do you need to make it for overlapping allowed? No, because there is no symmetricity, and for both of them the cases will be same. So both diagrams are exactly the same. Okay. So that's it about our FSM. We will see one more example that is very advanced. Okay, that is very advanced. So in this example, what you need to do? You need to design an FSM which will detect the sequence 1 1 0 0 1 0 1 0 and 1 0 1 1 0 0 1 in one FSM only. You need to design one FSM, only one FSM, which will detect 1 1 0 0 as well, 1 0 1 0 as well, 1 0 0 1 as well. Let me take an example. 1 1 0 0 1 0 1 0 1 0 1 0 0 1 0 0 1. Okay, so this is your input. This is your input, and this input I am giving to a FSM which detects these three sequence. So if I get any of the sequence, it will give me high output. So 1 1 0 0. This is the case for overlapping allowed. I am saying, okay, overlapping allowed. So 1 1 0 0 it will give me high output. Then 1 0 1 0 it will give me high output. Then again here also I can see 1 0 1 0, again it will give me high output. Again 1 0 1 0 I can see, again it will give me high output. 1 0 0 1 I can see, 1 0 0 1 I can see, again it will give me high output. Okay, then 0 1 0 0 nothing, 1 0 0 1 again I can see, again it will give me high output. So this FSM, what this FSM does, it will detect all these three combination. If in the input stream you are getting 1 1 0 0 or 1 0 1 0 or 1 1 1 0, it will detect all of them and will give high output. So this is what it means. Pause the video, try doing it on your own. I know you will get it wrong. Okay, there is no doubt about that. You will get it wrong only if you haven't studied it. But still, let's try it. Overlapping allowed, overlapping not allowed. Just do it for these two cases. Design for both of the cases. Design melee only. Okay, because melee is more important. Mostly melee is asked. More they will not ask. Okay, so anything you can design, but let's start with melee. Okay, So let's design melee only for this case, this is very rare. There is only 0.5% chances that this can be asked. But what if they ask it? So we are going to do one example. Pause the video. I will also pause the video, drink some water. Then I will come back and we will start analyzing this. Okay. So let's do it. You start doing it on your own and then we will see what we can do in this kind of questions. Okay then. Yeah. So let's see this example. So first we are looking at overlapping allowed. So we need to detect 1100, 1010 and 1001. So I will start from a random state, that is I am assuming state A. So first I will look at 1100. I need to detect 1100. So for that, if applied is 1, then I will go to state B. Applied input is 1, I will go to state C. If applied input is 0, then I will go to state D. Let's stop it here once. Okay. So if I am at B, that means 1 has been detected. If I am at C, that means 1 has been detected. And if I am at D, that means 110 has been detected. Okay. Overlapping allowed. This is the case of overlapping allowed. Mark that this is the case of overlapping allowed. Which is more difficult? Overlapping allowed is easy. Not allowed is easier than overlapping allowed, I guess. So we can solve in any manner. So let's do it. So if I'm at B, that means 1 has already been detected. If I'm at C, that means 11 has been already detected. And if I'm at D, that means 110 has already been detected. Now I need to detect 1010 in the same FSM. What do you think? Will I start from A? No. What is the first bit? First bit is 1 only. So if I have the state where 1 is already detected, so why I should not start from that state only? So I will start from B, because in B 1 has already been detected. Now my next task is, if 0 is coming, then I will go to next state, which is E, giving the output 0 only. Are you getting this point? Again, let's see it. I need to detect 1010 now. In state B, 1 has already been detected. In state B, 1 has already been detected. Here, this is my starting point. But why would I start from the starting point again? Why I am not starting from the starting point again? Because I know one thing, that my first bit has to be 1. My first bit has to be 1. So it is already there in state B. So I will start from state B only. No. So 1 has already been detected. In the next cycle, if 0 comes, then I will be happy and I will be going to the next state. Output will certainly be 0, because until I detect 1010, till that point I am not going to give my output as 1. So E means 1 and 0 has been detected. B means 1 has been detected, and E means 1 is already detected and then 0 is also detected. So E means 10 has been detected, right? Now you need to detect 101. So after 10, if 1 is applied, then I will go to next state. Basically the thing is, if the question was you need to design for this, how would you design? Starting from A, then I would go to B. If starting from A, if 1 is applied, I will go to B. Then if 0 is applied, I will go to C. And then if again 1 is applied, I will go to D. The same thing we are doing here. Just C is replaced with E. C is replaced with E. And D is replaced with F. You can check the same thing we are doing. 1, 0 and 1. 1, 0, 1. 1, 0, 1. At the last point, I will stop. Say yes or no. From 1 is detected, 0 is detected, 1 is detected. Here 1, 1, 0 was detected. Now in the last state, if 0 is coming, then what I will do? If 1 is coming, what I will do? That I will check. Okay. So E means 1, 0. And what does F mean? F means 1, 0, 1. Now if 0 comes, then what I will do? If 1 comes, then what I will do? That I will check. So this is the case for second one. What will be the case for third one? Third one will see if I am getting 100 anywhere, or directly 1001 anywhere. No, here you are getting 110, here you are getting 101. But are you getting 10 anywhere? Yes, I am getting 10 anywhere. So I will start from state E only, because already I am having 10. Now if my input comes 0, then I am happy and I can go to the next state, that is G. Say yes or no. So what G will represent? G is representing 1, 0, 0. This is 10 and another 0 is coming, so that means 100, G is representing 100. Now let's go to D. So across D, if 1 comes across D, after D if 1 comes, then what it will say? That sequence is not detected, your output will be 0 only, but I will look for the best possible case because I am in overlapping allowed. So what will be the best possible case? 101. Yes, I can see 101 here. I can see 101 in case of F. So I will go to F directly. Say yes or no. If my applied input after 110, if my applied input is 1, then sequence is not detected, but I will go to F because 101 I can already see. The best case is 101, which I can already see in F. Now in case of D, if 1100, if this is detected, if next bit is 0, so my sequence is detected now, 1100 is detected, the job for 1100 is done, but I will look for the best possible case because this is the case of overlapping allowed. So what is the best possible case? 100. Do I see 100 anywhere? No. Do I see 00 anywhere? Do I see 00 anywhere? No. Do I see 100 anywhere? Yes. I see 100 in case of G. So I will go to G. In case of G, I see 100. This is the best possible case. If 0 is applied, the best possible case is 100. So 100, where do I see? In case of G, I see 100. So if applied input is 1, sorry, if applied input is 0, after 110, if applied input is 0, then my output will be 1. Sequence is detected. 1, 1, 0, 0. Sequence is detected, but I will go to the state G because G represent 100. G is representing 100. So this 100 can be useful for me. So that's the cycle for first one, right? Let's think about the next one now. What will be the next? Let's think about G now. So at G I am having 100. At G I am having 100. If next bit is 0, if next bit is 0, what G will think? That sequence is not detected because job was to detect this sequence, but sequence is not detected. Now I will look for the best possible case. 000, do I see anywhere? No. 00, do I see anywhere? No. Single 0, do I see anywhere? No. I will have to go to the state A only. So now I will go to state A. Let's use another color of pen. So it will say that I will go to the state A. If applied input is 0, giving the output equals to 0 because sequence is not detected. Now, if the applied input is 1, if the applied input is 1, what it will say? That yes, sequence is detected, but I will look for the best possible case. Do I see 0001 here anywhere? No. Do I see 1001 anywhere? Do I see 01 anywhere? No. Do I see single 1 anywhere? Yes. I see single 1 in case of B. So if 1 is applied, my output will be 1 and I will be going to the state B. There you go. This is how you design it. Okay. Now let's think about the case. Let's pick this pen. Now let's think about the case F. So 101. If applied input is 0, if applied input is 0, you will say that yes, sequence has been detected because 1010 was my task. So if applied input is 0, sequence has been detected, but where will I go? Do I see 010 anywhere? No. Do I see 10 anywhere? Yes. I see 10 in case of E. So from F2 I will go to E. If my applied input is 0, giving the output equals to 1. Why output is equals to 1? Because sequence has been detected. If my applied input was 1, if my applied input was 1, that means sequence has not been detected. But I will look for the best possible case now. Best possible case is 011. Do I see 011 anywhere? No. Do I see 11 anywhere? Yes. That is the state C. So from F to C I will go. If my applied input is 1. But sequence is not detected, so I will give output 0. So here, how many ones you can see? If this state diagram was given in front of you, let's remove everything off. Let's remove all these off. But they will be used later on. So let's keep it. But forgetting about this 111 101 101 if this state diagram was given in front of you, would you be able to understand that how many sequences are detected here? You will see the number of ones. Number of ones, 1 time, 2 time, and 3 time. So that means certainly 3 sequence has been detected. If you see number of ones 3 times, 3 sequence has been detected. Then you can start from here. 1100, 1 1 0 0. What could be the other sequence? You start from here 1 0 1 0 1 0. You started from here 1 0 1 and then 0. So next sequence is 1 0 1 0. What about the next one? You can see here 1 0 0 0. Sorry. Yeah, 1 0 0 and 1. You see this cycle 1 0 0 and 1. So if I am moving ahead in the states, that means my sequence is being detected. So finally when it is becoming 1, at that time my complete sequence has been detected. So 3 times I can see 1, that means 3 sequences are being detected here. In the examination it is very rare that they will ask you this particular diagram. They will only ask what they can ask, that I need to design a FSM which will detect these 3 sequences which are 1100, 1010, 1001. How many flip-flops you will require? You need to design an FSM which will detect this given sequence. How many flip-flops you will require? How many states are there? 1, 2, 3, 4, 5, 6, 7. 7 states are there. Certainly you would require 7 states are there. That means you require 3 flip-flop. That would be your answer. That I require 3 flip-flop. Okay. So here I am going to write it. Total states are 7. This diagram is not completed, although total state 7, required flip-flop are 3. Tell me one thing, do you need to make this state diagram to get to know required flip-flop? No. I will just see A to B, B to C, C to D, then I will write down the conditions. Then I know next I need to detect 1 0 1 0. So 1 is already there, so 1 0 1 and another 0 that can be detected from the final state. And 1 0 0 1, so 1 0 is already there, so another state I would require. So I will get to know the state, directly I will get to know the state, right? Because I did not make the complete state diagram to name these states. We will see this example again in case of overlapping not allowed. There I will tell you, first I will make all the states only. I will make all the states only. There you can get to know that there will be 7 states only. Okay. But this diagram is not completed. Why it is not completed? Because we have taken only, if I am in state A and applied input is 1, then I will go to state B. But what will happen if applied input is 0? I will come back to state A only. What about B? What about B? If I am at state B, that means 1 has already been there. If applied input is 1, then I am going to the next state. If applied input is 0, I will look for the best case which is 0 only. So I will have to go to the state A. So if applied input is 0, then I will go to the state A. What about this? What about C? If applied input is 0, I am going to the next state. If applied input is 1, I will look for the best case which is 1 1. So I will come back to C only. So if applied input is 1, I will come back to C only. Okay. Come back to C. For D we have completely analyzed. For D we have completely analyzed. For 0 as well and for 1 as well. For F we have completely analyzed. For G we have completely analyzed. For E as well we have completely analyzed. For 1 as well, for 0 as well. If 1 is there, then 0 is there. This also we have analyzed. Oh, wait a second. In case of B as well we have analyzed that we don't need to go back here. Right? This is the issue. Really sorry for this mistake. In case of B, if 0 is applied, I am going to the state E, not to state A. Okay. In case of B, you can see if 1 is applied, I am going here. 0 is applied, I am going here. So state B is already analyzed. What in case of C? If 0 is applied, I am going here. If 1 is applied, I am coming back. Right? For state D, both inputs are there. State G as well, both inputs are there. For state F as well, both inputs are there. Okay. So that's it. This is the complete cycle. So this is how it will look. I know it is complex, but if they are asking any short question from it, you will be able to answer. That's for sure. But if you have studied it thoroughly, if you have put good amount of concentration, then you will be able to answer this as well. Let's try making for overlapping not allowed. It would be easy only. What I need to detect? 11001010, 1100, right? 11001010, 010, and then 1001, 1001. So let's start from A. First I will look at this sequence only. So if I am getting 1, I am happy. If I am getting 1 again, I am happy. If I am getting 0, I am happy. And at D I will see if I get 0 what I will do, if I get 1 what I will do. So here what I get to know that till B I am having 1, here I am having 1 1, and here I am having 1 1 0. So till this point I know that from D I can get 0 as well or 1 as well. So I don't require further stages. If I get 0, detected. If I get 1, then I will go back to some of the previous state. So here I require 4 states that I know. What about the next one? 1 0 1 0. So it will start from B only because 1 is already there. So it will start from B. So B to E it will go. B to E it will go. If applied input is 0. And if applied input is 1, if applied input is 0, output will be 0. And if applied input is 1, it will go to F. That means if it is at E, that means it is at 1 0. And if it is at F, that means it is at 1 0 1. So now if my applied input is 0, then sequence is detected. If my applied input is 1, then I will see what will happen. But certainly I do not require any further stage. So that also I know here. Say yes or no. Now what about the next one? Next one I require 1 0 0 1. So 1 0 is already there. 1 0 is already there. Right? 100 is there? No, 100 is not there. So 1 0 is already there. So what I will do? From E to G I will go. If applied input is 0. Here at G I am already having 100. 1 0 0. At G I am already having 100. If 1 is applied, sequence is detected. If 0 is applied, then something else will happen. But certainly I do not require any other stage. That's for sure. I do not require any other stage. That's for sure. So for that, I would know that I only require till stage G. So here I can get to know that I require 7 states. 1 2 3 4 5 6 7. I require 7 states. In case 7 state, I will be able to make it. Say yes or no. If it was Murray, then how many states you would require? If it was Murray, so this would be 1 0 0. G is 1 0 0. This would be 1 0 1, and this would be 1 1 0. So one stage for this, one stage for this, and one stage more for this. One more stage will be increased. Say yes or no. One more stage will be increased, because in case of Murray, you write down your output here only, and we already saw that in case of Murray, one stage is already increased. Why is that so? Because the final input also you need to apply, and then your output will be 1. So here in case of Murray, one more stage will be increased. So in case of Murray, you would require 10 stages, and for 10 stages you would require 4 flip-flop, right? So this you can tell. So this is the scene now. Now let's check for D, G and F. In case of G, it is 1 0 0. Okay. Now for D, if 1 0 1 is applied, if 1 is applied, I would get to know that I will not get my output 1. My sequence is not detected. So if sequence is not detected, certainly I will look for the best possible case. If sequence is not detected, certainly I will have to look for the best possible case. Do I get 1 0 1 anywhere? Yes. In case of F. So applied input is 1, then output is not detected. Until output is not detected, it will not be clear. Just as output is detected, then it will be cleared. Do you remember this point? Just as your sequence is detected, not output, sorry. Just as your sequence is detected, then it will get clear. If your sequence is not detected, it will not get clear. It will look for the best possible case only. So if I am at state D, and my applied input is 0, that means the sequence has been detected now. If sequence has been detected, then I need to start my journey right from the beginning. Say yes or no. So sequence is detected, so I will start my journey right from the beginning. So if my applied input is 0, then my output will be 1, and I am starting my journey right from the beginning. So this was the scene. Let's take the example of G now. So in case of G, we are at 1 0 0. So if 0 is coming, that means sequence is not detected, and if sequence is not detected, it will look for the best possible case. 000 not getting, 00 not getting, single 0 not getting, so it will have to go back to A only. So if my applied input is 0, my output will also be 0. But if my applied input was 1, I am at G, applied input was 1, then the sequence has been detected. And if the sequence has been detected, you need to start your journey from the A only, from right from the beginning. So it will go, it will not look for the best case, because this is overlapping not allowed. Just as it is detected, everything is cleared. If everything is cleared, that means I will start my journey right from the beginning again. So here only I am writing, if my applied input is 1, my output will also be 1, and I will be starting with A only. So this is how we can write with comma. If applied input was 1, then output will also be 1, and I will be starting the journey from A. Do you get this point? Yes, you understand this point. So this was the case for G. What about F now? In case of F, 1 0 1 is there. If applied input is 0, that means sequence has been detected and I need to start my journey from A only. If applied input is 0, sequence has been detected, I am starting my journey from A. And if applied input is 1, if applied input is 1, what I will do? I will look for the best possible case. 0 1 1, do I get anywhere? No. Double 1, do I get anywhere? Yes. I get double 1 in case of C. So the change of color should be there. So this was the case when 0 was detected, it was starting his journey right from the beginning. But if 1 is detected, it will start its journey from C. Why? Because sequence is not detected, and if sequence is not detected, it will look for the best possible case. And what is the best possible case? That is 1 1, and that you are getting in state C. So if applied input is 1, then output will be 0, but I will be starting my journey from stage C, because these 1 1 can be used for me. These 1 1 can be useful for me, so I will be starting here. So this is the diagram for overlapping not allowed. We can see the cases for A as well. For A, if applied input is 0, then it will come back to this state only. And what about C? If applied input is 0, it is going ahead. If applied input is 1, it will come back to this stage only. For B, already there are 2. For E also there are 2. E also there are 2. F also there are 2. And D also there are 2. So here also there are 2. So this is the final state diagram. Okay. Let's move all these off. So this is the final state diagram of a overlapping not allowed Mealy machine. Okay. So I know these are complex, but if they ask you to analyze this, will you be able to analyze this? Yes. You can tell that there are 3 times 1, 1, 2 and 3. 3 times 1, that means 3 sequence has been detected. How will you read it? You just need to go in the next state, 1 1, then 0 and then 0. So 1 1 0 0. And if they ask you whether it is Mealy or Murray, you can directly see it is Mealy only. Whether it is overlapping or non-overlapping, you will get to know just as the sequence are detected, they are starting right from the beginning. That means certainly it is non-overlapping. Overlapping is not allowed, non-overlapping. And if they are starting somewhere in the middle, just as the sequence is detected, they are starting somewhere in the middle, that means it is certainly your overlapping allowed. And this is overlapping not allowed. So this is the way we need to analyze it. We need to make this diagram. This is the maximum limit they can go. They are not going far from this. Okay, so that's it about from my side about FSM. We can see few questions on FSM. Purely on FSM, we will see some problems. So 5 to 6 problem we will see, that will be based on FSM only. So okay, and that will be a good practice for you. So probably I will be adding up those videos in this particular video only. Just in this particular video, in roughly around 20 to 30 minutes, we can finish off those problems. Okay, so in this particular video only, I will be adding up those problems, or I can make a separate video. I will check that, and with that, your FSM will be completed. Okay, then thank you very much. Hi everyone. So in this video, we are going to solve this particular problem, which was asked in GATE 2018 examination. Okay, a very good question it is, and a lot of people have given different solutions. So here I will try to give my solution. What should be a particular approach? Okay. But before starting the solution, you should watch one more concept, that is sequence generation. So I will add up the video of sequence generation right now only. So first we will see that particular concept of sequence generation, then only we will start the solution, because this concept is not usually taught at a lot of places. Like people generally do not teach this concept. So once watch that concept, understand what do you mean by sequence generation, how do you design a circuit of sequence generator. Once you are done with that, then come to this question. After that, it will be a kickbox for you. Okay, then you will realize that this question is based on sequence generation, not on FSM. Okay, so I will add up the video, watch that video, and then come back to this particular solution. Okay then, so let's see sequence generation now. Hi everyone, so now we are going to study about our next topic, that is sequence generation and detection. So first we will study about sequence generation. We will generate a particular sequence and then we will see how to generate a particular sequence. So sequence generation is a very simple topic, but sequence detection is a bit typical and also it is very important as well. And we will see the complete depth, and once you watch this particular video, after that there will be no confusion in sequence generation as well as in detection. First let's start with sequence generation. So what you need to do, you need to design a circuit. You need to design a circuit such that it generates this particular sequence, which is 1 1 1 0, then again 1 1 1 0, then again 1 1 1 0. So this sequence you need to generate. So what does that mean? That if first clock pulse come, if the first clock cycle is coming, then 1 should come. Then another clock cycle is coming, then another 1 should come. Then another clock cycle is coming, another 1 should come. Then another clock cycle is coming, 0 should come. Then another clock cycle is coming, 1 should come. Clock cycle 1, clock cycle 1, clock cycle 0. So in that manner it should go. So this one and this one, these are different. This one and this one, these are different. This one and this one, these are different. Certainly 0 is different from 1. That's for sure. Are you getting my point? With every clock cycle, 1, then again 1, then again clock cycle, again 1, then again clock cycle, then 0. So these ones are different. These should be denoted differently. So if I say, let's just say 1 is already different than 0. So if I say that if I introduce another bit, that is 0, and then I introduce another bit 1 in front of this. So now this one and this one are different, right? It is 1 1 and it is 0 1. But how will I differentiate this one? Either I will have to connect a bit 0 or I will have to connect a bit 1. So if I connect a bit 0 here, then these two are same. So that's an issue for me. And if I connect bit 1, then these two are same. So that's an issue for me. So using only one bit I cannot do it. But if I use 2 bits, then what I can do? If I use 2 bits, I can give 0 0 to this one, 0 1 to this one, 1 0 to this one, and 0 0 to this one. Now all 0 0 to this one, I can give anything. 0 0 I can give here, 1 1 I can give here, 1 0 I can give here. Here also I can give anything. I can give 0 1 to this one, 1 0 to this one, 1 1 to this one, or anything else. Basically I need to differentiate all these 4 bits. So 1 1 1 0. Now all these are different. All 4 different. Now what has your question become? Now your question has become that you need to generate a sequential circuit which will go from 0 0 0 1 to 0 1 1, then to 1 0 1, and then to 0 0 0, and then again back to 0 0 1. And here at the last bit, I will collect my output. So at the last bit I will collect my output. We will see the design, it will be more clear to you. So what did I do? I needed to generate this sequence 1 1 1 0. Then I got to know that my 1 is being repeated 3 times. So to differentiate that, I would need another 2 bits, 0 0 0 1 1 0, and for 0 I can connect anything. So this is the state diagram I am getting. Here there are 3 bits, that means I would require 3 flip-flops. 3 flip-flops required. So using D flip-flop I can design it. This counter I am going to design. This particular counter I will design, and across this bit, if I call this as Q2, this as Q1, and this as Q0. So across Q0 I will collect my final output. So first I will see 1 1 1 0, then again 1 1 1 0. Are you getting this point? We will design it, let's see. So now what has your question become? You need to design a counter which follows this sequence from 0 0 1 to 0 1 0 1 0 1 to 0 0 0. So this is how I am going to design. I am designing a synchronous counter. This is my synchronous counter. So I told you I have given the complete method how to design a synchronous counter, and we have seen a lot of examples as well. How do we design a synchronous counter? First we write down all the possible combination. So from 0 to I am going to 0 0 1. From 001 to I am going to 011. Then from 011 to I am going to 101. And from 101 to I am going to 000. And rest all these are don't care. So these conditions will not even occur. So these conditions are don't care. And what is D2? D2 is simply Q2 plus. What is D1? D1 is simply Q1 plus. And what is D0? D0 is simply Q0 plus. So these are don't cares. Right? Now my D2 will be function of Q2, Q1 and Q0. Same goes for D1, that will also be a function of Q2, Q1 and Q0. And same goes for D0, that will also be a function of Q2, Q1 and Q0. And if we write down the minterms, what are the minterms for D2? Minterms for D2 are 0, 1, 2, 3 plus don't care 0, 1, 2, 3, 4, 5, 6, 7. So don't care are 2, 4, 6, 7. What about D1? D1 has a minterm of 1 and don't cares are 2, 4, 6, 7. What about D0? D0 has a minterm of 0, 1, 0, 1, 2, 3 and minterms are 2, 4, 6, 7. Right? So I can make the K map now. This is how I will make the K map. Okay, and from there I can get the value of D1, D2, D1 and D0. So what is the value of D2? So here I can see a quad. So this process we have already studied, that's why we are moving a bit fast here. So this is a quad. What is constant here? Only Q1. Again saying I am having elaichi so that I do not cough. I am not a fan of Ajay Devgan. Okay. Again and again I am repeating it so that no one comments, sir, are you a fan of Ajay Devgan because pan masala? No pan masala. I don't eat these kind of things. Just I am having the elaichi. If you have the elaichi in your mouth, you will never cough will never come. So that I can explain the things better, right? So, what about D note? D note is Q2 bar only, right? D note is Q2 bar. So this is your D2, D1 and D note. So D2, D1 and D note. Okay. Now the thing is, you will design this particular circuit. This is the circuit, and here you will collect your output. This is your final output. Because what we wanted this sequence 1 1 1 0, and this is what you are going to get 1 1 1 0. But the thing is, you need to check whether it is going from lockout problem or not. Whenever we design a synchronous counter, we see what will happen to these states, whether it is going into lockout or not. So if it is going into lockout, then that will be a problem for us, because here we have assumed that it will be starting from 0 0 0 0. But what if it starts from 0 1 0? Where it will go? So since I am done designing this, now I will see whether I am suffering from lockout problem or not. So what will be my Q2 plus? Q2 plus will be equals to D2, and D2 is equals to Q1. What will be my Q1 plus? Q1 plus will be equals to D1, and D1 is equals to Q2 bar, Q1 bar into Q0. And what about Q0 plus? That will be equals to D0, and that is equals to Q2 bar. So Q2 plus is equals to Q1. So 1 0 1 1. Q1 plus is equals to Q2 bar, Q1 bar into Q0. So this is 0, this is also 0, this is also 0, and this is also 0. All these are 0. And Q0 plus is Q2 bar. So 1 0 0 0. So let's write it as 2. So from 2 to you are going to 5. What was the cycle? Here what was the cycle? I designed for 1 3 5 0. So what I designed? 1 3 5 0. 1 to 3, 3 to 5 and 5 to 0, and then came back to 1. This is what I designed. Now let's check. From 2 to 5 you are going. So 2 to 5 you are going. No issue here. 4 to 0 you are going. No issue here as well. 4 to 0 you are going. Here 6 to 4 you are going, 6 to 4, 6 to 4 you are going, again no issue. 6 to 4, then 4 to 0, again no issue. Then 7 to 4 you are going, 7 to 4 you are going. So 7 to 4 you will go, 4 to 0 you will go. So there is no another loop. There is only one loop, so there is no lookout. So the design is perfect. Design is perfect. So even if in the worst case, if it starts from 6, then after one clock cycle it will go to 4. Basically, if it starts from 1 1 0, so first you will receive 0 output, then you will receive again 0 output. After that you will receive again 0 output, and after that you will have the corrected output. That means 0 0 1, 0 1 1 and 1 0 0. This is what you are expecting. Then again 0 0 0, then 0 1 1. What we wanted? Triple 1 0, right? We wanted triple 1 0. So that you will be getting triple 1 0. So 5 is 0 1 0 1 actually. 5 is 1 0 1 and then 0 0 0. So the triple 1 0 you will be getting. You will be working in this loop only. You will keep on working in this loop even if you are starting from 6, 7, 4 or 2. Eventually you are going to fall in this loop only, and if you collect your output here, you will receive 1 1 1 0, again 1 1 1 0, and in that manner it will keep on going. Okay, so this is what this is how we can design it. So this was our first way of designing. But here what is the issue? You can already see, if you are designing a synchronous counter, there is very high chance that lockout problem may occur. So once your designing part is done, then after that you check that if there is a lockout problem or not, and when you find there is a lockout problem, you redesign it. So that is an issue for us. So that's also a good design, that's also one of the option, but there are other methods as well. So let's see method 2. So in method 2 I will be using asynchronous counter. So what I will be doing? So here you are not going to understand anything. Okay, so what I need to design? 1 1 0, this I need to design. Okay, now let's just say I have a up counter of 2 bits. So let's just say it's starting from 0 0, so then it will go to 0 1, then it will go to 1 0, and then it will go to 1 1. Now what I can do, this is the up counter, there will be 2 bit output, 0 0 0 1 1 0 1 1. So whenever you get 0 0 output, I will design a combination circuit here. I will design a combination circuit, and this will be my final output. So whenever I get 0 0 here, this should give me 1. Whenever I get 0 1 here, this should give me 1. Whenever I get 1 0 here, this should give me 1, and whenever I get 1 1 here, this should give me 0. Then again 0 0 would come, 1 1 1 0. So here what I will be having? 1 1 1 0, again 1 1 1 0, again 1 1 1 0. Is that a good idea? If you did not understand it, you will understand it certainly. Okay, no need to worry about that. So let's see the example. So same example we are taking, design a pulse train generator. So what I am going to do, I will design a up counter which gives me the following output. So this I am calling as Q1 and Q0. So my up counter will give me 0 0 0 1 1 0 1 1. Now at the output of up counter, I will be using another another combination circuit, which will give me for 0 0 it will give me 1, for 0 1 it will give me 1, for 1 0 it will give me 1, and for 1 1 it will give me 0. So this I will be using. Okay, so then with respect to these outputs, I will design a combination circuit which give me outputs respectively 1 1 1 0. So what will be my F? My F is simply Q1 bar plus Q0 bar, or you can say Q1 Q0 bar. F is Q, you can write the max terms, which is Q1 bar plus Q0 bar. So Q1 Q0 bar. So simple. What is this? This is your up counter, and here I am collecting my final output. So what will happen? First 0 0 will come, output will be 1. Then 0 1 will come, output will be 1. Then 1 0 will come. Here it is Q1 into Q0 bar. Q1 into Q0 bar. Then 1 0 will come, output will be 1. And then 1 1 will come, output will be 0. Then again the cycle will keep on going. Again 0 0 will come, output will be 1. Again 0 1 will come, output will be 1. Again 1 0 will come, output will be 1. Again 1 1 will come, output will be 0. So this cycle will keep on going, and at the receiver you will have 1 1 1 0 1 1 1 0 1 1 1 0 1 1 1 0 in that manner only. Are you getting this point or not? So that's the way it will go. So this is also a good idea, but here we were lucky, we did not have to use any clear or preset input. But what if this example is given? Try it on your own, you will understand what is the catch here. You need to generate this sequence 1 1 0 1 1. This sequence you need to generate. First tell me how many flip-flops will be required. Look, here there is no concept that you need to differentiate these stages, that I need to differentiate this guy and this guy. There is no concept like that. Why is that so? Because each states are different. Each states are different. With respect to one stage, I am getting one output. With respect to other stage, I am getting another output. Basically, what do I mean is that if I design an up counter, which is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So with respect to this I will be getting 1, with respect to this I will get 1, then I will get 0, then I will get 1, then I will get another 1. So this is what I need. If this stage comes, what I am going to do? I am going to clear it. Say yes or no. Here I will clear it. This I don't want. So I want my output to go from 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0. Just as I get 1 0 1, output should be cleared. Are you getting this point? So number of bits in the sequence are 5. That means at least 5 you need, at least 5 combination you need where you can assign the output. At least 5 combination I need. The number of bits in the sequence are 5. If the number of bits were 4, here number of bits were 4. So I thought that at only 4 sequence I need. And if I need only 4 combination I need, and to each combination I can assign a value. So using only 4 combination I can assign these values. But now I have number of bits equals to 5, which are 1 1 0 1 1. So I need at least 5 combination to whom I can assign the value. At least I need 5 combination. So for using 5 combination, for getting 5 combination, how many bits you require? 3 bits. And 3 bits means 3 flip-flop. Did you understand this point or not? I am designing it using asynchronous up counter. Okay. Number of bits in the sequence are 5. So what do I know? That each bit I will be assigning to a particular combination. I will be assigning 1 to a particular combination, then again 1 to another particular combination, then again 0 to another particular combination, then again 1 to another particular combination, and then again 1 to another particular combination. So I need at least 5 combination. And if I need at least 5 combination, then from 2 bits I can get only 4 combination. But from 3 bits I can get 5 combination. Usually there are a lot of formulas which are taught in this particular method, but we are not covering any formula here. We will not see any formula. We will think, okay, you are designing it using asynchronous counter. That means you are either designing up counter or down counter. Then you will use a clear input. Also, you know one thing, that is that if I am designing it using up counter or down counter, that means each combination is getting a particular output. 0 0 0 1 0 1 1 1 0 1 0 0 0 1 1 1 1 0 0 1. That means I need at least 5 combination. If I need 5 combination, that means required flip-flops are 3. Okay, well and good. I hope this is clear to you. So what I am going to write? Q2, Q1 and Q0. With respect to that, I will have my output F. So these combination I can write. Okay. So if 0 0 comes 1, 0 0 1 comes 1, 1 0 0 1 0 comes 0, 0 1 1 comes 1, 1 0 0 comes 1. After that, what should be your F? F I am saying. There is a up counter. Okay, 0 0 is coming, F should be 1. Basically this is the scene, that there are 3 output bits. This is your combination circuit, this is your up counter. So 0 0 is coming, 0 0 0 is coming, output should be 1. 0 1 0 is coming, output should be 1. 0 1 0 is coming, output should be 0. 0 1 1 is coming, output should be 1. 1 0 0 is coming, output should be 1. But in this up counter I will use a clear input which will make sure that these conditions do not even occur. Say yes or no. This clear input will make sure that these conditions do not even occur. Why is that so? Because let's just say if 101 is occurring, this 101 is occurring. So after one clock cycle 101 will occur, and I do not even want this. I do not even want 101 to occur, because I want this sequence to be repeated. 11011, then again I want to go back here. Say yes or no. Right, so this is the sequence I want. So I make sure that these conditions do not even occur. So all these will be don't care. What will be my clear input? Here I am going to break it, right? This here I am going to break it. So this condition I do not want. What I don't want? Q2, Q1 and Q0. 1 0 1. So there I told you a trick, and I also told you when that particular trick will be applicable. When it will be applicable, you are designing a up counter. Okay, where you are starting from? If you are designing up counter, that means you are supposed to start right from the 0. Are you starting from 0? Yes, I am starting from 0. That means trick is applicable. Now if you are designing up counter, up means you are high in your life. If you are high in your life, that means you will only look at 1. So if I am only looking at 1, so I need to design clear input. So what I will write? Q2 into Q0, and Q2 into Q0, 1 into 1. I want my clear input to be high. So 1 into 1 is 1 only. So my clear input is high. So this is the ideal design of clear input. What is the ideal design of clear input? This is the ideal design of clear input, which is Q2 into Q0. Say yes or no. Right? So this is my clear input. I hope you already know this thing, because we have already studied this in a very in-depth manner. We spent around 2.5 hours just to understand this particular concept. When this trick is applicable, when this trick is not applicable, that we have seen in very in-depth manner, right? What about F input? Do you need to make a K-map here? What do you think? What about F? Do you need to make a K-map? No. What do I do is that all these don't squares are there. I can consider all these as 1. If I consider all these as 1, then I will be left with only one max term, that is 0 1 0. So I can write my F is Q2 plus Q1 bar plus Q0. There you Q2 plus Q1 bar plus Q0. This is your final output F. Okay, so this I will be removing. So you should have a good aptitude that 1 1 0 1 1 is there. These are don't care. I can assume any value. If I assume one value here, I will be left with only one max term. So that will be Q2 plus Q1 bar plus Q0. So that will be my F, and this will be my clear input. So this is how I will be designing it. You can see this is the clear input. What is the clear input? Q0 into Q2. So Q0 into Q2 is fed as the clear. So how do we design it? That also you know by the trick, and trick is applicable if you are starting right from the 0. And if you are designing up counter, that means you will be focusing on 1 only. So if I focus on 1, Q2 into Q0 is giving me 1. So that's it. So this is my clear input. Okay, this is my clear input. And what about this final F? This will be my output, final output F. So my final output is Q0 plus Q1 bar. From here Q1 bar would be coming, and from here Q2 is coming. So here I will receive my final output. So if first clock cycle comes, here you will have 0 0 0. So what you are going to have? 1. Then you will have 0 0 0 1, again 1. Then you will have 0 1 0, then you 0, then again 1, then again 1, then again this cycle will come here. So this is how you can design. Okay, so this was the method 2. The third method is using shift register. So that we have already seen with the help of an example when we were studying shift register. Okay, you can see the example. So this much knowledge is more than enough for gate aspirants. They can give this particular circuit and ask you the output, that which sequence it will generate. For gate aspirant, they will give this particular circuit and they will ask you what will be the sequence generated. So you can directly see that, okay sir, this is a down counter. Actually it is a down counter, but I need to make it up counter, so I will use this. Also I can use this here as well. Okay, so now it is up counter. In the previous design, did I make it up counter or down counter? Okay, it was up counter only. So here also we are using up counter only, so I should make it up counter. So this is a up counter. You will get to know that it will start from 0 0 0, it will keep on going. Then you will see where it is being cleared. Okay, it is cleared at 1 0 1. So if it is being cleared at 1 0 1, that means it is being cleared at 1 0 1. Yeah, right, it is being cleared at 1 0 1, so that means that will not occur. So it will count from 0 to 4 only. If it is counting from 0 to 4, so what will be your output? 1 1 0 1 1, then it will keep on going. So if you can design, then certainly you can analyze that well, right? You can certainly analyze this particular circuit, right? So that's it about our sequence generation. Very easy topic, very straightforward topic. Let's see some common gate question which has been asked. So the minimum number of JK flip-flops required to construct a synchronous counter with the count sequence 0 0 1 1 2 2 3 3 and then 0 0. So 0 0. So in that manner they ask 0 0 1 1 2 2 3 3. So how would you show 0 at 0 only? How would you show 1 at 1 only? How would you show 2 in binary? That would be 1 0 1 0, and this would be 1 1, this would be 1 1. Now you need to differentiate this 0 and this 0, this one and this one. Look, 0 and 1 are already different, you do not need to differentiate it, but both 0 0 are same, you need to differentiate it. And we are using synchronous counter, so we are using first design. So this is the design we are using, this design we are using. In synchronous counter we need to differentiate everything, right? We need to differentiate all, and then we design a counter, and with respect to that we get our output. So if we are using synchronous counter, then we need to differentiate everything. Okay, so 0 and 0 both should be differentiated from each other. How I can differentiate it? Using 1 bit only, 0 and 1. Can I differentiate these two as well? Yes, using 1 bit only, 0 and 1. Then these two also should be differentiated, 0 and 1. These two also should be differentiated, 0 and 1. But here you are using 3 bits, so here also you need to use 3 bits only, no? Are you getting this point? If I am using 3 bits here, so here also I will use 3 bits. So what I should do is that first I should denote 0 0 and 1 in 2 bits, then I need to differentiate. So this I will put 0 1, this I will put 0 1. Basically here 1 is repeated twice, 0 is repeated twice, 2 is repeated twice, and 3 is repeated twice. So differentiate 2 times. What I can do? I can add a bit 0, I can add a bit 1. So both are different now. So using only 3 bits, how many bits are required? 3 bits required. That means 3 flip-flops are required. That's it. Okay. Solve the next question on your own. 0 1 0 2 3. 0 1 0 2 0 3. So for 3 you would require 2 bits, that I know. So certainly I will denote all the numbers in 2 bits only. So this and this are already different, this is also already different, this is already different. What is the scene? Scene here is this 0 0. So these I need to differentiate. These I need to differentiate 0 0 0 0 and 0 0. Can I differentiate it using 1 bit only? If I connect a 0 here, this would be 1, and again I need to connect either 0 or 1. If I connect 0, this would be same, and if I connect 1, then this would be same. So using 1 bit only I cannot do it, so I need to use 2 bits. So if I use 2 bits, that means this will be 0 0, this will be 0 1, and this would be given 1 0. You can give anything to these, 0 0 you can give, 0 0 here also you can give, 0 0 also here you can give. So how many bits you need to use? 4 bits. And what does that represent? 4 flip-flop. So what is the answer? 4 flip-flop. If the question was in this manner, okay, try answering on your own. How many flops you will be requiring? What do you think? So it is 0. For 3 you would require 2 bits, so 0 0, then 0 1 0 1 0 1 0 1 1 0 1 0 and that is 3 1 1. So you need to differentiate between these two and these 4. So what do you think what you will do? You need to differentiate 4. If you need to differentiate 4, then at least you require 2 bits 0 0 0 1 1 0 1 1. So all 4 are differentiated. Anything you can give here. Now what about this? If I give 0 0 here, at least I need to give 0 1. Apart from 0 0, I can give anything, and here also I can give 0 0. So how many flops you require? 4. Directly you can see that it is coming for 4 times. If it is coming for 4 times, then at least I would be requiring 2 bits to differentiate these 4. It is coming 2 times, then at least I would require 1 bit. But here I would require 2 bits. So 2 bits for this and 2 bits to represent 3. So 2 plus 2, 4 bits you require. So answer will be 4 flip-flop. I hope you are understanding it. To represent the numbers, I need 2 bits. Because if I am getting state 3, then at least 2 flip-flops has to be there. From only 1 flip-flop you can get 0 and 1 only. So if I need state 3, then at least 2 flip-flops has to be there. So if 2 flip-flops are there, okay, it is fine. Now you need to differentiate 1 1 1 1. So 2 bits, 2 bits, 2 bits, 2 bits. All these are done using synchronous counter. All these are done using synchronous counter. So that's the scene. In synchronous counter, what do? We generate the states and then we design the counter. But using asynchronous, what is the scene? Using asynchronous, the scene is, let's just say you need to generate this pulse using asynchronous. So what you will see, there are 4 bits in the sequence. So if there are 4 bits in the sequence, if I take any up counter or down counter, so with respect to each combination, I will assign a particular bit. So if there are 4 bits in the sequence, that means I need to take 4 combination. So for 4 combination, what I will be requiring? 2 flip-flop. In this case, I require 5 combination. For 5 combination, I will be requiring 3 flip-flops. There you go. Okay, so that's how you will be solving it, right? So that's it. Very easy questions are asked in the GATE examination. Even in the interview, they will not focus much on this. They can just ask a simple question and generate this particular sequence. They will not even ask whether using synchronous counter or asynchronous counter. They will just ask, you need to generate this particular sequence. Will you be able to generate it? Yes, certainly you will be able to generate it. And if I had been the student, I will be using asynchronous counter because that is a much easier design. The only thing is here you will have to design the clear input. So if I need to design a clear input, so that also I can do quickly because I have the trick. So I will start right from the 0, and by using the trick, I will design this clear input as well, and F is already visual. Okay, so better I will be designing with this method rather than going for synchronous counter. Okay, synchronous counter also I can take, but that may take some time. But here also in synchronous counter, the problem of lockout can also occur. So better I will be designing in this method. Okay, so that's it about our sequence generation. So I hope you must have visited our sequence generation. You must have understood how to generate a sequence using synchronous counter, using asynchronous counter by both. Okay, let's start this problem. In this problem, what they are saying, a traffic signal cycles from green to yellow, yellow to red, and red to green. Okay, in each cycle, green is there for 70 seconds, yellow is there for 5 seconds, and red is there for 75 seconds. So you are going from green to yellow, yellow to red, and then red to green. This is how you are going. But this is there for 70 seconds, this is there for 5 seconds, and this is there for 75 seconds. Okay, now what they are saying, a very important line will come. The traffic light has to be implemented using a finite state machine. The only input to the FSM is a clock of 5-second period. Okay, there is only one input, that is a clock which is of 5-second period. What do you understand by that? In a FSM, there is always an external input and a clock, right? But here what do we see? Here we see that there is only one input, which is clock only. So based on clock only, you need to analyze this cycle. You need to make this cycle based on clock only. And clock has a frequency of, or you can say time period of 5 seconds. It has a time period of 5 seconds. So I will just make it So this is a particular circuit I am having, and it is having a clock which has a time period of 5 seconds. So this is your FSM, this is what they are calling. But there is no input, no external input. Now what do you think what will happen here? So I will assume clock as a button. So I am pressing a button. That means initially green light should turn on. That button will be there for 5 seconds. I will again have to press the button. Then again green light should turn on. Because green light should be there for 70 seconds. Say yes or no. In first clock cycle, there should be green light. Then again there should be green light. Then again there should be green light. In that manner green light should go. After some cycles, when 70 seconds have been completed, after that yellow light should turn on. Yellow light is turning for only one clock cycle. Then yellow light will turn on. Then again if I am pressing the button, again one more clock pulse is coming. Then red light should turn on. Now this red light will turn on for 75 seconds. That means a lot of clock pulses will come. Clock pulse, clock pulse, clock pulse, clock pulse. So in that manner it will go. So now your question becomes is that you need to make a circuit which generates this sequence, that you go from green to green, green to green, green to green, green to green, then yellow to red, red to red, red to red, red to red, and then again back to green. So this is the question. Did you understand this point or not? You have only clock input. With every clock pulse, your output will change. Clock pulse will come, output will change. Clock pulse will come, output will change. But for the first clock pulse, you want green output. Then another clock pulse, you want again green output. Another clock pulse, you want another green output. We saw the questions, no? That you need to generate 0, 1, 0, 2, 0, 3 in that manner. That first clock pulse, you should generate 0, then 1, then 0. Or we saw these examples. That in first clock pulse you need to generate 0, then another clock pulse you need to generate 0 only, another clock pulse you need to generate 0 only, another clock pulse you need to generate 1. So in that manner you need to go, right? We have seen these examples. So now what is our task? Our task is just to design this. So what is the sequence required? Green, 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 then yellow, red, 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 then red. Now why I have written 14 times here? Because green is there for 70 seconds. Green is there for 70 seconds, and yellow is there for 5 seconds, and this is there for 75 seconds. Now in one clock pulse will come, that is of 5 seconds. One clock pulse is of 5 seconds. One clock pulse is of 5 seconds. So that will be there for 5 seconds. Then another 5 seconds, another clock pulse will come. So till 14 clock pulse, 70 by 5, till 14 clock pulses, 5 by 5. Till 1 clock pulses it should be yellow, and till 15 clock pulses it should be red. Are you getting this point? First clock pulse comes, green. Second clock pulse, green. Third clock pulse, green. Till 14 clock pulse it should be green. So 14 into 5, 70. Then 1 clock pulse will come, yellow. Then another clock pulse comes, red, 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 till 15. And then you again need to come back here. So this I forgot to make here, that I again need to come back to green. So this is the cycle: green, 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 yellow, red, 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 and then in that manner. Okay. Now your question is, you need to generate this sequence. We have two methods, using synchronous counter, using asynchronous counter. So let's design it using asynchronous counter. So what I am going to design? I am going to design it using asynchronous counter. So how will I design? Let's not see the solution first. How will I design? Using asynchronous counter. In asynchronous counter, what do we do? Do you remember? Do you remember this sequence? 0, 0, 0, 0, 1. Do you remember this sequence? How did we generate it using synchronous counter? What did we do? That 0, 0, 0, 1 we wrote. Then we got to know that these 3 0 are different. All these 3 0 are different. We need to differentiate them. And to differentiate these 3 zeros, what I need to do? 0, 0, 0, 1, 1, 0. And this is already differentiated, so I can put 0, 0. So how many flops you required? 3 flip-flops, right? Now what is the scene here? Green, yellow, red. 3 guys are there. Okay. All 3 are different. Green, yellow, red. All 3 guys are different. So what I can do? I will call green as 0, 0, 0. Green as 0, 0. Yellow as 0, 1. This is my yellow. This is my green. And red as 1, 0. and this is my red. Because 3 guys are there. To represent 3 guys, I need 0, 0, 0, 1 and 1, 0. Say yes or no? Correct? Okay. Now the scene is, first I need green, then another green I need, then another green I need. In that manner, 14 times I need green. 14 times. Then I need yellow, one time only. And then I need yellow is 0, 1. And then I need red. How many times? 15 times. Say yes or no? Till this, everything is clear. Green, yellow, red, all three are different. I am representing 0, 0, 0, 1 and 1, 0. 14 times I need 0, 0, 0, 0. Then one time I need 0, 1. And again 15 times I need 1, 0, 1, 0, 0. Say yes or no? Understood? Everything is crystal clear. Now, till this point everything is clear. So now we can go to the next page. So this is everything I have written. Green is 0, 0, yellow is 0, 1, red is 1, 0. So 14 times 0, 0, 1 times yellow, and this is red. So this was green, yellow, red. Now what I am gonna do? These all 14s are different. No, with every clock pulse, these cycles should come with every clock pulse. I am gonna design a synchronous counter. So I will give one clock pulse, then something will come. I will give another clock pulse, then another combination will come. Let's just say in first clock pulse this combination is coming. Then in the next clock pulse this combination may come. Any another different combination can come. Basically all these are different. All these 0, 0 are different. Now I need to differentiate it. If I need to differentiate these 0, 0, how many bits I require? Tell me. There are 14 combination. 14, 0, 0 are there. 14, 0, 0 are there. And I need to differentiate all of them. So how many bits I would require? To differentiate two zeros, I would require only 1 bit. 1 and 0, both are different now. To differentiate 3, 0, I would require 2 bits. 0, 0, 0, 1, 1, 0. All are different now. To differentiate 5 zeros, I would require 3 bits. Because from 2 bits, I would do only this thing. Now, I will have to give 0, 0 to this. Now, these two are becoming same. So, that I don't want. So, I would require 3 bits here. So, I would take 3 bits. 0, 1, 1, 1, 0, 0. If it is there for 14 times, using 4 bits, what I can do? Using 4 bits, I can generate 16 combination. Using 4 bits, I can generate 16 combination. 0, 0, 0, 0, 0, 0, 0, 1, both are differentiated. 0, 0, 1, 0, this is also differentiated. Then 0, 0, 1, 1. In that manner, I will keep on going. And any combination I can pick. Just I am not going to repeat the combination. Okay, I am not going to repeat the combination. That's it. So here I am going to pick from 0, 0 I am starting, and this is 14 times. So this would be my 12 or 13. From 0, 0 I am starting. Then 0, 0, 0, 1 I can put. Then 0, 0, 1, 0 I can put. Then 0, 0, 1, 1 I can put. Then 0, 0, 0, 0, 1, 0, 0 I can put. So these combination I have. After that I am going to put 0, 0, 1, 1. Then I am going to put 0, 1, 0, 0. Right? So I have differentiated all these 5 bits. Say yes or no? So 5 bits I have differentiated. If I need to differentiate the 14th bit, then I would require 13 here. That is of no use actually. That is of no use. You just understood that here 13 means 1, 1, 0, 1. Okay. And this would be 12. So what did you understand here? You just understood one point, that is to differentiate these two bits. These 0, 0, 0, I require another 4 bits. And for this I would require only any combination would work because this is already differentiated. Now all these are same. Again all these are same. And to differentiate them, how many combination I would require? Since this is occurring 15 times. This is occurring 15 times. And using 4 bits I can generate 16 combination. So yeah, using 4 bits I can differentiate them. Using 4 bits I can differentiate them. So anything could come here, and basically this could be our 14. Right? Any combination I can define. Basically I have different 16 combination. I have 16 different combination. Using those 16 different combination I can differentiate them. So now what I am gonna do? I'm gonna design this counter. That will be a tough task, but I'm gonna design this counter. Then I will pick only these two bits outward, these two bits out. So this is what I'm gonna do. I design this counter. Okay, it will have 6 bits. So how many flops are required here? 6 flip-flops. 6 flip-flops. So I will design this counter, synchronous counter made using 6 flip-flops. Here we are having 6 bit output. There will be a clock. Now for the first cycle, clock is triggered, 0 0 0 0 will come. So here you will have 0 0. If you are having 0 0 here, then this will be lit, and here I will connect a LED, and the color of LED will be green. So in the next cycle, what will come? 0 0 0 1 0 0. I have designed the counter in this manner only, 0 0 1 0 0. What I have designed is that this is my initial state, some q I am writing, then my q plus will be 0 0 0 1 0 0. In that manner I have designed it. So in the next cycle, what will come? 0 0 0 1, again 0 0 here. So again 0 0 is coming, then again this is lit. In the next cycle, these values will change, but these will be constant at 0 0 for 14 clock cycle. For 14 clock cycle, these will be constant at 0 0. So these two will be constant at 0 0 for 14 clock cycle. So till 14 clock cycle, always this green LED will be lit. Say yes or no. Are you getting this point or not? This is how I am going to design using synchronous counter. This is not the end of the solution. Okay. Here our answer is saying that it should be 6 flip-flop. Now after 14 cycle, what will happen? After 14 cycle, this will come 0 0 0 0 1. After 14 cycle, 0 0 0 0 1 will come. 0 0 0 0 1 will come. So which one will be lit? This is a 2:4 decoder. So what decoder will do? Now D1 will be lit. So D1 will be lit. So this LED I will keep as yellow. Okay, this LED I will keep as yellow. After that, what will happen? In the next cycle, what will come? In the next cycle, 0 0 0 1 0 will come. 0 0 0 1 0 will come. 0 0 0 1 0 will come. That means this LED will be lit. This LED will be lit. So I will keep this LED as red. This will be my red LED. Why this is my red LED? Because at 1 0, if this cycle is coming 0 0 1 0, red should be lit. So now in the next cycles, what will happen? These bits will change, but these bits will be constant at 1 0 only. So always this will be lit, red will be lit. So what will happen? At each clock cycle will come, clock cycle will keep on coming till 14 clock cycle, green is lit. So at the output, this will be my final output. This I will keep in a box. This I will keep in a box, and that will be my final output. Now someone will ask, sir, what about 1 1? What about 1 1? Sir, what about 1 1? I will not even design it. In my counter, I will design in a manner that this 1 1 condition never even occurs. So this bit will go needless. So this I will not show at the output. I will not show at the output. So this will go needless. There is no use of this. Okay, I will design my counter in a manner that just as I reach here, I go back to this state. Okay, in that manner I will design my counter. Just as I reach here, I go back to this state. So 1 1 is not even occurring. So that condition will not even occur. So in that manner I will go, and this is how it will be lit. Green, green, green for 14 times, then yellow for 5 seconds, and this red for 15 seconds. So how many flops I am using now? So the answer that is coming out to be is 6 flops. But is that the best design? Answer that is coming out to be 6 flop. Is that the best design? This is my question. Sir, as of now we cannot comment if that is the best design. Sir, design it using asynchronous counter, then we can tell, sir, whether it is a best design or not. So now I am going to design it using asynchronous counter. Okay, going to design using asynchronous counter. So which sequence is required? This sequence is required. Green, 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 yellow, red, red, red. This you have already understood. So this sequence is required. So what we do in asynchronous counter? What do? We will design either up counter or down counter. We have solved all the examples using up counter only. So here I am going to design up counter only. So first I will design up counter. First I will design up counter that has how many combination? How we used to solve using asynchronous counter? How we used to solve? Let's just say I need to generate this sequence. So what I would used to do, that I would design 2-bit up counter 0 0 0 1 1 0 1 1. Then I will design a combination circuit. So if my 0 0 is coming, my output should be 0. If my 0 1 is coming, output should be 0. If 1 0 is coming, output should be 0. If 1 1 is coming, output should be 1. And then I go back to this stage. So again 0 0 is coming, output should be 0. 0 1 is coming, output should be 0. 1 0 is coming, output should be 0. And 1 1 is coming, output should be 1. So your counter will give you these outputs 0 0 0 1 1 0 and 1 1. And with respect to that, that particular combination circuit will give you 0 0 0 1 output. Say yes or no? You remember this example, right? Or shall I show it to you again? I hope you remember it, but again I am showing it. Where it was? Here it was. So we were designing, we need to generate 1 1 1 1 0. So first we designed the counter, first we designed the up counter. With respect to that, we were having 1 1 1 1 1 1 output and then 0 0. So what this counter would be doing? You will start from 0 0, you will start from 0 0 1, then again 1, then again it will throw 1 and then 0. So here I was collecting my final output. So I was getting 1 1 1 0 1 1 1 0 1 1 1 0. Now tell me one thing. Where we were, here we were. Okay. So this is what we were doing. Now I will design up counter again. How many combination I total need? Total combination, how many total combination I require? 30 combination, right? 30 combinations required. Why 30 combination? Basically for 0 0 0 0, let's just say for 0 0 0 0 0, I can give green. Then 0 0 0 0 1, I can again give green. 0 0 0 0 1 0, I can again give green. 0 0 0 0 1 1, I can again give green. So in that manner, I will give green green green. Then for one time I will give yellow, and then for rest of the time I will give red. So I require at least 30 combination. Say yes or no? I require at least 30 combination. यार भाई, अब इन मक्खी का क्या बोलें यार? वेलकम टू राजस्थान. एक तो एसी ऑफ करके पढ़ाना पड़ता है, तो आप लाइक जरूर करना इसको. यू डू लाइक इट. ओके. Usually my subscribers are English guys, so I have to speak in English. So do like this particular video. Yeah. So what I was saying? So I was saying that we need to generate 30 combination such that to each combination I can give my output. So I will design up counter such that I get at least 30 states. Not at least, such that I get exact 30 state. Exact 30 states. So my target is to design mode 30 up counter. I need to design mode 30 up counter. Okay. I need to design mode 30 up counter. How many flops are required? 5 flip flops are required. Okay. So for mode 30, if I need to design mode 30, that means I need to use clear input. Use clear input as well. Because a standard counter will count from 0 to 31. That would be mode 32 counter, right? If I am using 5 flip flops, I will generate mode 32 counter. I will generate mode 32 counter. But if I need mode 30 counter, that means I need to use clear input. So that also I need to use. So how we will use clear input, that also I will show. But this is how I will design my binary up counter. This is my up counter only. Q0, Q1, Q2, Q3, Q4, these will be my outputs. Now, what I will do? So these combination I will generate. I will give one clock pulse. If I give first clock pulse, what I will have? 0 0 0. Then I will give another clock pulse, what I will have? 0 0 0 1. Then I will give another clock pulse, what I will have? 0 0 1 0. Till 14 clock pulses. Till 14 clock pulses. What is this? These numbers are 14. From 0 to 13. That means 14 combination. So till 14 clock pulses, my green light should be lit. So I am designing a combination circuit such that if these are the inputs, then it should give me 1. And I will connect the LED which is green only. Okay, I am designing my combination circuit in a manner that if these are the inputs, green should be 1 and the LED will be green the way we have connected here. Now after that, what I am doing, I am designing a combination circuit such that if this is the input, if this particular input is there, then it should throw yellow light. It should throw yellow light. Only one combination. Here it should throw green light. And for this, how many combinations are there? 0 to 13, 14, 15 to 29. Why 15 to 29? If you count from 15 to 29, there will be 15 combination. 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So there are 15 combination. 15 combination. And with respect to each combination, I need to throw red light. So I am designing my combination circuit in a manner that that particular combination circuit will have minterms from 0 to 13. So 0, 1, 2 till 13. For yellow it will have the minterm of 14 and for red it will have the minterm of 15, 16 till 29. 30, 31, 32 you do not want. That means in your counter, just as you reach 29, your 30 should be cancelled. 30 should be cancelled. So what is my 30? 30 will be Q5, Q4, Q3, Q4, Q3, Q2, Q1 and Q0. How do we get 30? 1, 2, 4, 8, 16. 28 and 2, 30. Yeah. So I get 30 in this manner. So what will be my clear input? This trick I have told. This trick is applicable only at specific places. What all are those places? That also I have told. Right? If you are starting right from the 0, this trick is applicable now. So clear input will be Q4, Q3, Q2 and Q1. So I will design my counter in a manner that it counts up from what to what? It counts up from 0 to 29. At 30 it should be cleared. So here it should be cleared. Okay. So now it will be cleared. And clear bit is Q4, Q3, Q2 and Q1. Okay. So this should be cleared. So this is how we usually show it, that this should be cleared. Q4, Q3, Q2, Q1. Okay. Now counter has been designed. These outputs I will have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 0. These outputs I will have, and these outputs will be fed to a combination circuit which will generate me these outputs. So basically this will be the final design. This is my binary up counter using 5 flip-flop. This is the clear input. These outputs will be generated. Now these will be fed here. These outputs will be fed in this manner. Here and here, then they will be fed here as well. All will be fed here as well. Or then they will be fed here as well. In that manner, all will be fed. Then we are having combination circuit. What they are doing? So if these bits are fed to it, then they generate output 1. Which minterms are fed? Should be fed 0 to 13. If these minterms are fed, then they will generate output 1. And if they generate output 1, it will give a green light. So this light should be green. So what I am going to do is that this should also be clocked. So here I am telling this is my clock. Okay. This is my clock. So what I am going to do is that I am going to put this complete design in a box. Okay. This clock will be my one of the input. Clock will be input as well, but I cannot show it one page only. In one page it is very tough to show. So this clock will be my input. I will keep on giving the clock. Then I would know that this is my binary up counter. It will generate the output. Then these outputs will be fed to this combination circuit. This combination circuit, if these are the minterms, if here I am generating 0, 0, 0, 0, 0, 0, 0, 0, 1 till 13, green light will be lit. After that, at 14 minterm, 14, yellow light will be lit. And for minterm 15 to 29, which light will be lit? Red light will be lit. Red light will be lit. So in that manner we will go. Okay, so this is my final design, and here how many flip-flops we are using? 5 flip-flops. So what they asked, minimum number of flip-flops, the minimum number of flip-flops. So the answer would be 5. In the examination, I do not need to make this final design. In the examination, it will not take me 30 minutes to solve this problem. In the examination, what I will see? Okay, this question is based on sequence generation only. So this is the sequence I need to generate. So total 30 cycles I would require. How would I know that I would require 30 cycles? 75 seconds, 5 seconds, and 70 seconds, 5 seconds, and 75. 70 plus 5 plus 75. What that would be? 150. And 150, each cycle is of 5 seconds. So basically 30 seconds, 30 cycles I require. So 30 combination I need. With respect to each cycle, with respect to each combination, I can give 1 bit of output. So 30 combination I need, and for making the 30 combination I require 5 flip-flops. That would be the answer. That's it. And then I will get to know that if I design it using synchronous counter, then green, yellow and red, they have to be defined as per the bits as well. Then green should be given 0 0, yellow should be given 0 1, and red should be given 1 0. So if they are also defined as 2 bits, then to differentiate, then I will require 4 bits. So this is making me use 6 flip-flop. But if I am using asynchronous counter, then I get to know that if I am using asynchronous counter, then I get to know that this is my required sequence and I need 30 combination. And if I need 30 combination, what does that mean? That I require only 5 flip-flops. 30 combination means 5 flip-flops only. Okay. So if I require 5 flip-flops, I will generate 30 combination, and with respect to those 30 combination, I can generate my different outputs, which will be green, 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 then yellow, then red, red, red. So in the examination, within 30 seconds, if my concept is clear, I will write down my answer, that is 5 flip-flop. So it is possible to design it using 6 flip-flops as well. This is the design, and but it is possible using 5 flip-flops as well. So these outputs are fed in this manner. These outputs are fed in this manner, and this is how you are generating it. Okay, so this is the complete answer. This is the complete analysis. I hope you enjoyed it. If you enjoyed it, consider sharing it with everyone, with your teachers as well. Everyone, like, it is always better to learn. Everyone can learn. So this I designed on my own. I thought that this is the way it should be designed. So this is the best possible solution as per me. If I get to see something else, if I get to learn something else, if someone is also posting something, if someone gets some good point, then also he can add the good points. So yeah, that's it from my side. I will look more into it. If I get better design, then I will try to make a better design. But this question is framed by IITs, so certainly they must have thought of this design only. Okay then, yeah, thank you very much. Hi everyone, so now we are going to solve this assignment. So one by one we will see the questions. So let's start with the first one. So state diagram of FSM is the state diagram of a FSM is designed to detect an overlapping sequence of 3 bits. It is shown in the below diagram. The FSM has an input pin and output pin. The initial state of FSM is S0. Okay. So if the input sequence is 1 0, this sequence is there starting with the leftmost bit. This is the leftmost bit. Then the number of times output will be 1. So which sequence it is detecting? So we just need to go forward. We just need to go forward. When we are going forward, what did I get to know? First my input applied is 1. Then my input is 0. And then my input is 1. Just as I get input 1, my output is 1. That means this sequence is detected. Sequence detected. Which sequence is detected? 1 0. If I apply input 1, then output is 0. Then 0, output is 0, then 1. Just as the applied input is 1, sequence is detected. So it is detecting 1 0 1. Say yes or no. It is detecting 1 0 1. So if it is detecting 1 0 1 and it is overlapping, so how many times output will be 1? What do you think? Look, 1 0 1 you can see here once, then another 1 0 1 you can see here twice, then 1 0 1 1 0 1 thrice, 1 0 1 1 0 1 1 0 1 and 4 times. Basically you can see 1 0 1 4 times here, right? So output will be 1 4 times. Are you getting this point? 1 0 1, then again 1 0 1, then here again 1 0 1 and 1 0 1. Overlapping sequence, output is 1 for the 4 times. That's it. That's the answer. Okay. I told you one thing when we were studying the theory, that always move forward. Move forward. Don't see when I am coming back. Nah. Just move forward. Forward, forward and forward. 1 1 1. Sorry, 1 0 1. There you go. Okay. Well and good. Let's solve the next one. Here transitions are made. From A to B you are going for a particular set of input, from A to C you are going for a particular set of input, B to A you are going for a particular set of input, B to C you are going for a particular set of input. Inputs are X, Y and Z. So X, Y, Z can take 8 values, right? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. In that manner 8 values it can take. So based on that we will proceed. So now they are saying transition from state A are ambiguously defined, transition from state B are ambiguously defined, transition from C are ambiguously defined, all the state transition are defined unambiguously. Let's just say I don't know the meaning of ambiguous. Like it is very easy word. Ambiguous means what do we say? Like one which is not defined properly. Ambiguous means which is not defined properly. But even if I don't know the meaning of ambiguous, let's just say in the examination I don't know the meaning of ambiguous, how I will be proceeding in this particular problem? So what I would see that X, Y, Z are the input. I need to go from A to B or B to A. Basically I am transitioning between A, B and C. A to B I can go, B to A I can come, A to C I can go, C to A I can come, C to B I can go. So I am transitioning between these based on the input X, Y, Z. So what I am going to do, I am going to make a table where, let's just say if my present state is A, X, Y, Z can take 8 values, right? X, Y, Z can take these values. So based on that I will define what will be my next state if my present state is A. So if your present state is A and applied input is, if Y is 1, if your present state is A, Y is 1, then do not think about anything else. If Y is 1, then certainly you are coming back to state A only. So if Y is 1, where Y is 1? Y is 1 here, you are coming back to A. Y is 1, you are coming back to A. Y is 1, you are coming back to A. Y is 1, you are coming back to A. This is one of the transition. This is one of the transition. This is one of the transition. If your Y is 1, then forget about X and Z. If Y is 1, then X and Z don't care, you are certainly coming back to stage A. This is what they are saying. Now what else they are saying? If X is 0 and Z is 1, if X is 0 and Z is 1, then you are coming back to stage A only. You are coming back to state A only if X is 0, Z is 1. X is 0 and Z is 1. That means you are coming back to state A. X is 0, Z is 1. X is 0, Z is 1. Already you are coming back to state A only. Here it was written that you are coming back to state A, and this transition is also asking you to coming back to state A only. So this is correct. There is no issue. But if this transition was asking you to come to state B, then there is an issue. Because one input cannot tell that I will go to A and I will go to B. Let's just say I am standing at A and I tell my FSM that my applied input is 110. So either it can go to B or it can come to A. Both cannot happen. But in this case, in both of the transition, I see two transition. When Y was 1, don't care about X and Z. When Y was 1, don't care about X and Z, A. Now, when X is 0 and Z is 1, don't care about Y. X is 0, Z is 1. X is 0, Z is 1. Don't care about Y. You are coming back to A only. So till this point, there is no issue. Right? Let's see for next ones. Now, when X is 0, Y is 0 and Z is 0, then you need to go to state B. X is 0, Y is 0, you need to go to state B. There we are going. Okay. What else is there? When X is 1 and Y is 0. When X is 1 and Y is 0, you need to go to state C. When X is 1 and Y is 0. X is 1 and Y is 0. X is 1 and Y is 0. Do not care about Z. X is 1, Y is 0, you need to go to state C. So all the transition I have defined from state A. From state A. From state A, I could come back to state A only. I could go to state B. I could go to state C. So all the transition I have defined from state A. From state A to state A, state A to B, state A to C. Do you agree to my point? Okay. Just one more thing I want to add here. Just one more thing I want to add here. It is not important as per the problem, but what I am doing here is that I am going from A to A to B, and A to C. A to A, if I am saying that this probability is P1, this probability is P2, and this probability is P3, then think on your own, take your own logic and tell me what will be the value of P1 plus P2 plus P3. This has nothing to do with this particular problem, but this is a good concept which will be used in further problems. If you are at state A, you are coming to state A, going to state B and going to state C. For any applied input, only these three possible cases are there, right? For any applied input, if I apply 0, 0, 0, then either I can come to A, or I can go to state B, or I can go to state C. So these probability will be 1. Say yes or no. This we will again take care. Okay, let's drop this particular concept here. We will again see this concept, but I hope you must have understood. If you are leaving state A, then there are 3 chances that you are coming back to A, or going to B, or going to C. So all the probability will be in addition to 1 only. Okay, now let's do the same concept for B. So what we are going to do, from B we will check. So transition from B we are checking. If y is 1, do not care about anything, come back to state B only. If y is 1, do not care about anything, come back to state B. Come back to state B. No issue there. Okay. What else they are saying? If y is 0 and z is 0, go to state A. Y is 0, z is 0, go to state A. Y is 0, z is 0. Y is 0, z is 0. Y is 0, z is 0. Go to state A. Go to state A. Y is 0, z is 0. Go to state A. Do not care about x. Okay. What else they are saying? Going here, going in, and here. What they are saying? If y is 0, z is 1. If y is 0, z is 1, go to state C. If y is 0, z is 1. Okay. Y is 0, z is 1. Do not care about x. Go to state C. Go to state C. So here also there is no ambiguity. You don't know the meaning of ambiguity. You are just solving the problem. This is how you are writing the next state. So if applied input is 0, 0, 0, next state will be A. Applied input is 0, 0, 1, next state will be C. Applied input is 0, 1, 0, next state will be B. Applied input is 0, 0, 0, 1, 1, next state will be B. This I am writing from these states only. So there were only 3 ways to go out: to A, to C, and coming back to B. That we have checked. Now let's do the same thing for C. Let's do the same thing for C. If my current state is C, then what will be my next state? So I am at C now. So if z is 0, do not care about x and y. If z is 0, do not care about x and y, come back to C only. If z is 0, come back to C, come back to C, come back to C, and come back to C. This is what they are saying. Okay. Now what else they are saying? Now they are saying that if z is 1 and y is 1, then go to B. Z is 1 and y is 1. Z is 1. Z is 1 and y is 1. Where else? Z is 1 and y is 1. Z is 1 and y is 1. Z is 1 and y is 1. Then go to state B. This is what they are saying. Still there is no ambiguity. Right? If z is 1, y is 1, go to state B. Now what they are saying? Here what they are saying? If x is 1 and z is 1, go to state A. X is 1 and z is 1. X is 1 and z is 1. Then go to state A. Initially what they were saying, that if your z is 1, then do not care about anything, go to state B. Now what they are saying, if x is 1 and z is 1, go to state A. So with respect to one input, you are having 2 possible output, which is not possible. Here there is ambiguity. So what I would be doing in the examination is that I would be solving this, that I would get to know that there are 3 inputs x, y, z. Based on that there will be transition. So this is what I will make. That currently I am at A. Based on the transition I am going to these states. Currently if I am at B, based on the transition I am going to these states. Currently if I am at C, based on the transition I am going to these states. But I get to know that at one of the place I am going to 2 states, which is different. So I could tell that C is ambiguously defined. In the examination, even if I don't know the meaning of ambiguous, ambiguous means not correctly defined. That is a very easy word. But even if I don't know the meaning, then also I can tell it, because this is something different. Okay, that's why I always tell in the examination, do not drop a question from where, like from the topic where you are most comfortable. Like if I am comfortable in FSM, and if there is some word whose meaning I don't know. Still I will try to figure out the problem there. Okay, I will try to figure out the problem. I will try to proceed in that problem, and something I will certainly find out. Something I will certainly find out. So here I found out that from C to B I am going, and C to A I am going for the same amount of for the same input. That means that is ambiguously defined. There you go. Okay. Now let's see this question. A is the initial state. Which sequence is detected? So what did I tell you? Always proceed in forward path. So initially 0, 0, 1, then wait a second, 0, 1, 0, 1, and then 0. I am going forward, 0, 1. If I stop at B, in both cases I am getting 0. Then if I stop at C, in both cases I am getting 0 output. If I stop at D, in both cases I am getting 0 output. Even if going out, basically, okay, D is not defined properly, only going out is defined. Okay, coming in is also defined. Basically, at D if you apply 1 input, then you are going here. At D if you apply 0 input, where will you go? So this diagram is not complete. At D, if I am applying 1 input, I am going to state E. But if I apply 0 input, where will I go? That is not defined here clearly. So I need to check the diagram again. Yeah, this is shown as this. Okay, 0, 0. So this was not correctly defined. Now it is correctly defined, right? So if I'm at D, then even if applied input is 1 or applied input is 0, still I am getting 0 only. So I will move forward. Now if I'm at E, so if I'm at D, then that means I would have reached initially 0 is applied, then 1 is applied, then 0 is applied. So at D I am having 0, 1, 0. And at E what I am having? 0, 1, 0, 1. Now what do I see? If I apply 1, then I am getting output 0. If I apply 0, then I am getting output 1. So that means this is detected. Are you understanding how we are proceeding? Let me make it again for you. So I start from here, from A. This is my initial state. I get to know that if applied input is 0, then also there is an issue. If applied input is 1, that also is not correctly defined. This is also not. If applied input is 0, then output is also 0. If applied input is 1, then also output is 0. So I am starting from here. I am starting from here. Then I went to B. Applied input is 1, applied input is 0, output is always 0. Applied input is 0, applied input is 1, output is always 0. Applied input is 0, output is 0, applied input is 1, output is still 0. But I will go forward now. Once I reach to E, we have already designed it, then analyzing it should be easy for you. I guess this is easy for you. When I reach E, what do I see? If applied input is 1, then there is an issue. But if applied input is 0, then it is detected. There you go. So it is detected. So what is this? This is your detected sequence. Sequence detected. Okay. It is Millet or Murray. You can directly see it is Millet. Right? It is overlapping or non-overlapping. What do you think? When I reach the state E, at state E, what is the scene? So starting from 0, 1, 0, 1. So at state E, this is the scene. If 0 is applied, then sequence is detected. And if 1 is applied, then it goes here. So let's just say this is the case of overlapping not allowed. If overlapping is not allowed and 0 is detected, then what it will do? Overlapping not allowed. Overlapping not allowed means everything will be clear and it will start its journey right from the beginning. If overlapping not allowed, but it is starting its journey from D. It is starting its journey from D. That means if applied input is 0, it is still looking for the best possible case. What is the best possible case? That is 0, 1, 0. You can directly see here that is 0, 1, 0. So that's why it is going to D. That means certainly here overlapping is allowed. Overlapping allowed. Okay. Because if overlapping was not allowed, then after getting one output, after getting the sequence, it would have started its journey right from the beginning. But this is what it is not doing. It is still looking for the best possible case. That means certainly there is overlapping allowed, right? Because it can use this 0 1 0 in the next cycle. So this 0 1 0 is useful for it, right? Next question you will solve on your own. Solve on your own. So here, until I get output 1, I am not happy. I will keep on moving. So I will keep on moving forward. 1 0 1 0. Here I am getting output 1. So at E, what is my scene? 1 0 1 0. Just I get 1 0 1 0. This is the sequence detected. Just I get 1 0 1 0. That means my output is 1 now. 1, if I detected 1, my output was 0. If I detected 0, my output was 0. If I detected 1, my output was 0. If I detected 0 again, then my output was 1. So this is the sequence detected. Now it is Millet or Murray? It is Murray. You can directly see it is Murray. Now tell me one thing. What is that you will tell? You will tell whether it is overlapping or non-overlapping. That means overlapping allowed or overlapping not allowed. What do you think? So if I am at state E 1 0 1 0, here only everything happens, right? This will decide, final state will decide. Now if applied input is 0, then where it is supposed to go? Sequence is detected. I am assuming overlapping not allowed. This is what I am assuming. If this diagram was for overlapping not allowed, then what would have happened? That it will forget this, and now it will decide based on this 0. So based on this 0, it will look for the best possible case. What is the best possible case? Here we don't know what is there. At B 1 is detected, at C 1 0 is detected, at D 1 0 1 is detected, and at E 1 0 1 0 is detected. So it will look for the best possible case. For 0, what is the best possible case? 1 1 0 1 0 1. So for 0, best possible case is A only. So no worries, it is going to A only, right? But if there was 1, then it would look for the best possible case, but only for this 1. It will forget this. It will forget this particular sequence because this has been already detected. If it is detected, so it will forget this. Now it will only see that where is my 1. So it would have gone to B now if overlapping was not allowed. But if overlapping is allowed, then what it will do? It will look for the best case from here. Do I get 0 1 0 1? 0 1 0 1 anywhere? No. Do I get 1 0 1 anywhere? Yes. I get 1 0 1 at D. So it will go to D. And this is what it is doing. So it is taking back the previous sequence. It is taking the use of the previous sequence. But if overlapping was not allowed, then it would have forget this sequence. Just as it is detected, you forget it. In case of overlapping not allowed. But here overlapping is allowed. That's why it is taking the reference of the previous bits as well. So it is going to state D. So this is your Murray and overlapping allowed, right? Overlapping allowed. So till now this thing has not been asked in GATE examination yet. That they just give the sequence and they ask only this thing, that which is the sequence that is detected. But now they can ask whether it is overlapping allowed or overlapping not allowed. Very, very important concept, and high chance that it will come. Okay, like my intuitions are saying that certainly it is about to come. Overlapping allowed, overlapping not allowed, that you need to tell. So you will be able to tell. Just you go to the last state and then you will see whether it is taking the reference of the previous bits or it is not taking the reference of the previous bits. Okay, so that we need to check, and we have seen it in a very in-depth manner. Let's see this question. Very good question it is. Okay, so this particular sequence is given. A is the initial state. Which of the following sequence produces high output more than once? This is what they are asking. Now in all these questions, you are getting high output only once. You are getting high output only once. So in the examination, if the question is coming on sequence detection, then your first task should be to check how many times you are getting high output. Okay, here I did not tell this thing, but I should have told this thing, that you are getting high output only once. That means only one sequence is detected. We saw this example when we were studying FSM. In the last we saw this example where 3 sequences were detected and only one FSM was there. What about this? Initial state is A. So you go from here to here, 1, 1 and again 1. A to C if you are going, that means 1 is there. A, C to D if you are going, that means 1 is again there. And then at D what you are seeing, that if again 1 is applied, then output is 1. So 1, 1, 1. This is the sequence detected. Are you getting this point? Did you understand this point? This will be the summary of our complete chapter of the sequence detection, which is one of the most complex concept, but we are looking it in a very good manner. I will start from A. I will go to C, that means 1 has been detected. If I am going to D, that means 1, 1 has been detected. At D, what do I see? If applied input is 0, then it is going to some other state. If applied input is 1, then it is giving you output 1. That means at D, if 1 is applied, then sequence is detected. Now it is overlapping or non-overlapping. What do you think? It is overlapping or non-overlapping? If it was non-overlapping, then what would have happened? Just as it detects the sequence, it will start its journey right from the beginning again, if it was non-overlapping. But it is overlapping, right? How you can say it is overlapping? Because it is looking for the best possible sequence, and here you can see what is the best possible sequence, that is 1, 1, and 1, 1 you are getting at D. So certainly when 1 is applied, it is coming back to D only. Okay, so that is correct, crystal correct, that if it was non-overlapping, then just as it gets 1, 1, 1, everything will be cleared and it will start its journey right from the beginning. But it is again looking for the best possible sequence, which is 1, 1 only. The best possible sequence is 1, 1, which it is getting at D. So it is overlapping, right? Let's see the next one. When again I will start from A, and when you are getting your 1 again here, so what is the scene here? 0. Once applied input is 0, so at B I am getting 0 only. At B I am getting 0 only. And at B, if I again apply 0, then output is 1. That means this is the sequence detected. And if I apply 1, then I go to C. That is different thing. At B, if I again apply 0, then sequence is detected. So this is the sequence detected. And if I apply 1, I am going to different state. Now tell me whether it is overlapping or non-overlapping. If it was non-overlapping, then it would have started its journey right from the beginning again. Basically, at B, if you are having 0, then you know that if 0 is applied, that means sequence is detected. So I need to forget this now. So I will again go back to A. Right? But it is looking for the best possible sequence. What is the best possible sequence for it? That is single 0. And single 0 it is getting at B itself. So that's why it is coming back to B only. So it is overlapping. So non-overlapping and overlapping you can find very easily, right? In case of melee. In case of melee, it is very easy. Because just as the sequence is detected, if it is not going to the initial state, that means it is it is overlapping. If it is not going to the initial state, that means it is overlapping. And if it is going to the initial state, that means it is non-overlapping. Okay. So just as the sequence is detected, it should go to the initial state. Then only we will say it is non-overlapping. Otherwise, it is looking for the best possible combination, best possible sequence. That means it is certainly overlapping. But in case of Murray, it is a bit different. In case of Murray, if it was non-overlapping, where it was going? In case of Murray, at state E, 1010 has been already detected. Now, if next state is 0, then it will look for the best possible case of 0. That means it will start from A. But in case of 1, what it will see? That I will start from B, right? Again, it is non-overlapping. This is the case of non-overlapping. It has already forgot 1010, but the new bit applied is 1. If the new bit applied is 1, then why it should start from A? Why it should start from the beginning? It will see if I am getting 1 at any other place. Yes, I am getting 1 at B, so I would have started from B. still it is non-overlapping, but it is starting from D. It is starting from D. If it is starting from D, what does that mean? It is starting from D. What does that mean? That it is looking for best possible case considering these 3 bits. Okay, it is looking for the best possible case considering these 3 bits. That means it is taking this in action. So this is your overlapping. So this was the case of overlapping. So what I am gonna do is that I will just copy this same diagram. I will just change this. How I will change this is that Arja bhai. So now if input 1 is applied, then now I am going to state B. Okay, so sequence still detected is 1 0 1 0 1 0 1 0. Sequence still detected is 1 0 1 0. But now you need to tell whether it is overlapping or non-overlapping. This is your non-overlapping now, right? Why it is non-overlapping? Because after 1 0 1 0, if 1 is applied, if it was overlapping, then it would have seen this particular sequence, that is 1 0 1. So it should have gone to D. But now it is going to B. It is going to B. What does that mean? If it is going to B, that means that it is only looking at this bit. It has forget these 4 bits. So just as it is detected, forget it. I will only look at 1. So 1 means I will start my journey from B. Say yes or no. Okay. So in case of Murray, it's not necessary that you will start from here. You can start from other place as well. You can start from B as well. But either from A or from B only you will start, because you will forget all other bits. Only one bit will be there. It could be 0 or 1. If the bit is 0, that means if bit is 0, that means no sequence is detected. This 1 can also not be your best possible case. 1 0 can certainly not be your best possible case. So if bit is 0, then your best possible case is A itself. So you are going at A. But if your bit is 1, then your best possible case is B. So that's why you are going to state B. Okay. So that you need to take care. So this is your non-overlapping allowed. Okay, non-overlapping. This is what I am writing. So you will not get confused now, right? In case of Murray, in case of Milley, it is very straightforward. In case of Milley, it is very straightforward. In case of overlapping, it can start from any random state, but in case of non-overlapping, it will start right from the beginning. But in both of the cases, it is not starting right from the beginning. That means it is certainly overlapping. So both are overlapping. This is also overlapping and this is also overlapping. Now we need to detect the sequence. So in first case, what I can detect? 1 1 1 and 0 0 0. So I will start from here 1 0 1 0. So 0 0, this is detected, right? Then again 0 0, this is again detected. So twice it is detected, right? So more than once they are asking. What about this? Here I need to detect 1 1 1 and 0 0 0. So here I can detect 0 0. That's it. This is all I can detect. 0 0 I can detect. 1 1 1 I cannot detect. Anything else I cannot detect. So this is the thing that I can detect now. What about this? Here I can detect 1 0 no. Here I can detect 1 1 1. Right? Then again I can detect 1 1 1 again, because this is overlapping allowed. 1 1 1 again. So here I am getting twice. What about the final one? What I need to detect? 0 0 or 1 1 1? Nothing I can detect. Nothing I can detect, right? Neither I can detect 0 0, neither I can detect 1 1 1. So nothing I can detect. So only A and C are correct. Are you getting this point? A and C are correct. So this is the solution. So I hope now the things are getting more clear to you after studying this particular concept, which is sequence detection. Very complex concept. That's why it is ignored by teachers as well as the students. But everything we are looking for it. And believe me, like my high intuitions are saying that this topic will come in your examination, be it 2025 or 2026 or 2027. This topic is about to come, because this is not asked properly. Okay, I have seen this question from FSM in 2018 as well, in 2019 as well it was there, in 2022 it was there certainly, and in 2024 it was not there as far as I remember. So basically they are asking the question, now they are asking the question from FSM. So this is the topic they are focusing on. In 2018 as well there was question, 2017 there was question, 2019 as well there was question. So they are focusing on this topic. So the question may come, this topic is left, that which topic is left? Overlapping one, overlapping or non-overlapping. Also, whenever they ask this question, there was only one sequence detected, every time. But two sequence can also be detected in one state diagram only. We have seen the state diagram where three sequence was detected. So what you just need to see that how many times my output is being high. So my output is being high for 2 times. Well and good. Yeah, so let's see this question. Last question it is. It was asked in GATE 2022. So a state transition diagram with state ABC are shown and the transition probabilities are shown, P1 to P7. For the state diagram, you need to select the correct statement. Okay. So what did I tell you? At any random state I am, let's just say this is the random state S0. So what did I tell you? For any applied input, either I can come in or I can go out. Or just going out I am showing by one arrow only. There could be multiple arrows. So for any applied input, if I am standing at S0, so for any applied input, either I will come here, come back to S0 or I will go out. Is there any other possibility? Some people will say that, sir, you can come to S0 from other state as well. Yes, but that will depend on S1, no. That if I am standing on S1, then either I can come back to S1 or I can go out. But this probability, if I am calling it as Px3, this has nothing to do with these two cases. This has nothing to do with the guy standing on S0. If some guy is standing on S0 and you apply x1 input to it and it is coming back in, and you apply x2 input to this guy, it is going out. The guy is standing at S0. If you applied x1 input to it, it is coming in, and if you apply x2 input to it, it is going out. So only two things he can do if he is standing at S0. What is coming in to S0? It has nothing to do with that. The guy has only two chances. If applied input is x1, I will come back. If applied input is x2, I will go back. This example we took, that's why I made this complete table. So if I am at state A, for the given inputs, I can either go to state B or to C or come back to A. So all these probabilities combined will be 1. Are you getting this point? People get confused in this particular case that they will say that, sir, what about this Px3? It has nothing to do with that. If you are at state S0, for applied input x1, you are coming back to S0. For applied input x2, you are going out. Where you are going, that doesn't matter. So Px1 plus Px2 is equals to 1. That's it. Now in this case, let's see. If I am standing at A, that means either I can come in, that is P7, or I can go out, that is P1 and P4 plus P1 plus P4, that is equals to 1. It has nothing to do with this P3 that is coming in and P6 that is coming in. You need to stand at A. If I am at A, for some applied input x1, I am going to state A only. For some applied input x2, I am going to state B. For some applied input x3, I am going to state C. This is what they are saying. If applied input is x7, I am coming back to state A. If applied input is x4, I am going to state C. And if applied input is x1, I am going to state B. Say yes or no. Right? Now, write down the second one. Now we will write down for state B. This was for state A. State A. Now, if I am standing at state B, that means for any applied input, I can either come in or go out, which is P3 only. So P2 plus P3 is equals to 1. This was for state A. This was for state B. Let's write down for state C. Either I can come in for any applied input. If x5 is applied, I will come in, or I can go out. If P6 is applied, x6 is applied, then I will go out. So this was for state C. So what do you see here? P1 plus P4 plus P7 is equals to 1, and P2 plus P3 is equals to P5 plus P6. That's it. And this is also equals to 1 only. Are you getting this point? So this diagram you will remember. Say yes or no. That if I am at state S node. For any applied input, I can go in or go out. Look, there could be multiple inputs. For that, you can come in as well, right? For x1 input, you can come in. For x2 input, you can come in. For x3 input, you can go out. For x4 input, you can go out. For x5 input, you can go out. But from some other state, with some x6 input, you are coming to S node. But that doesn't matter, because for this particular arrow, you must be in some S1 state. So if you are standing at S1 state and x6 is applied, then you go to S node. So that doesn't matter here. So I will just make it in this manner, that some x6 is applied. So that doesn't matter. If you are standing at S node, then come back to with x1 you are coming back to there, with x2 you are coming back there, with x3 you are going out, with x4 you are going out, with x5 you are going out. So what do you see from here? That is x1 plus x2 plus x3 probability plus probability of x4 plus probability of x5 is equals to 1. Okay. In the examination, you could have thought of it. I did not study this concept before, like when I was attempting this particular question, because I attempted this GATE 2022 examination only, but I did not study it before. But still, I was able to think that if I am at state A, there is only two chances, whether I could come back or I could go out. So there you go. P7 plus P4. I got to know that would be 1. P2 plus P3. Sorry. P7 plus P4 plus P1 would be 1. P2 plus P3 would be 1. P5 plus P6 would be 1. So from there I could tell these options. Okay. So that's the end of our FSM. And that's the end of our sequential circuits. Okay. So sequential circuit is completed. Now there is one small concept left, that is static time analysis. So STA we are going to study now. I hope you enjoyed sequential circuit. If you enjoyed it, let me know in the comment section or in the WhatsApp group. Just let me know how the content was. Okay. Thank you very much. Let's meet you in the next lecture. There probably we are going to start static time analysis. Okay. Thank you very much.